Okay, so day 2. So we've been talking with no sound. So apparently, that wasn't good. We didn't.
It's early. It's very early.
It's early.
We've been awake for a long time.
Sandy, where are you? We need you. Our whole run of show is messed up without you in the room, apparently. So we're gonna start all over because we were talking without any sound. So first of all, to get us started, before we redo our introductions, if you can just put in the questions section, where you're joining us from, maybe how you heard about this event today, and then also anything, any experience that you've had with the GAVRT project. So we would like this to be a very interactive session, and we imagine folks are going to be coming in and out throughout the entire event. So let's see, good morning, Sandy from Pasadena. Sandy was it, just so you all know, if Sandy Marshall was in Apple Valley, we would have not started without sound.
Yes, we miss you, Sandy.
We miss you. Okay, so we'll go ahead and do introductions. Maureen, you want to get us started?
Yeah. So I'm really happy to be here with you, Lisa. My name is Maureen Anderson. I'm a scientist at the NASA Jet Propulsion Laboratory over in Pasadena. I'm a radio astronomer, astrophysicist, and I'm excited to be here today to talk all about the sun and the eclipse.
Yes. And I'm Lisa Lamb. I'm the president and CEO at the Lewis Center. Working on the GAVRT project is one of my favorite things that I get to do. And we're excited to talk about all aspects of the GAVRT project overall, share the science that the data that we're collecting during the eclipse, and ways that you can get involved in the future in GAVRT as well. So, and then as I was saying when I was muted, we have some really special guests on today. So thank you all for getting up so early and joining us. Marin has a really special guest who's on.
Hi, Mom.
Marin's mom is joining us. We have 2 of our esteemed board members, Yolanda Carlos and Marisol Sanchez Alvarez. Thank you guys for getting up so early and joining us. And again, we'd love to hear where the rest of you are joining from. So we have Sarthak from India.
Awesome.
Oh, you heard about us at AAS. Great. And Manas. Oh, Glee. Very cool. I just heard about your project. I'm very interested in learning more about it. Yeah. So, okay. Do we want to explain a little bit about what we're seeing on the screen?
Yeah, so what we're looking at here is what our operators are viewing as they're getting ready to observe the solar eclipse. What will show up on the right, which right now just looks like a dark blue box, but that's where our maps of the sun will appear. And it will look different than what you're typically used to seeing when you look at the sun, either with your eclipse glasses on, if you're looking at it directly yourself, or if you're looking at an image of the sun from a space telescope, for example. What we're looking at is the sun at radio frequencies, and specifically between 3 gigahertz and 14 gigahertz approximately. So the sun will look a lot different. It'll have a lot lower angular resolution, which just means that the size of things that you can resolve in the image is much larger compared to what maybe you're used to with an optical telescope. It'll be the disk of the sun at gigahertz frequencies, and the exciting things will be what are called active regions, which are bright spots on the radio sun, representative of regions in the corona or atmosphere of the sun directly above. It's early in the morning and I haven't had my coffee yet. I'm forgetting the word. Features on the surface of the sun on the photosphere, where you see dark patches where you have cooler regions of plasma. And above those, you have active regions, which are portions in the corona above those patches on the surface of the sun. And those are the active regions. Those are the things that we're targeting in our radio maps. So they'll appear in the image of the sun as a brighter spot where you're getting more flux. And those are the things that we're going to probe with really high angular resolution during the actual eclipse. So the moon's limb will pass over the solar disk, and it'll pass over those active regions. And the act of the moon's limb passing in front of those active regions while we collect data is what's going to give us really high angular resolution. So typically with our radio telescope, which we'll talk more about later, we have arc minute resolution, but we'll get an improvement by multiple orders of magnitude by using the moon's limb to give us, so allow us to probe higher spatial scales, finer structures in those active regions. So that's what you'll see on the right. Over on the left, we just have some diagnostic information. We can see where the telescope's pointing. There's a coordinates box on the left showing the azimuth and elevation, basically the place in the sky that the telescope's looking at, and some other diagnostic information. We can see what day of year it is. It's day 287 in 2023, and the time in universal time, UTC. So local time, it's about 7:15 in the morning here in California.
Bright and early. Well, 7:15 doesn't seem so bright and early, but it's bright earlier. Okay. All right. So our team is on standby, ready to start. When are we actually going to start observing?
Yeah. So the eclipse doesn't start happening till approximately 7:45 here. So it's going to be about another 30 minutes before the eclipse actually starts. So we're waiting to take data until that time. So we're going to start taking data during something called first contact, which is when the moon's limb first contacts the solar disk. So that's when we'll start targeting those active regions I was talking about. We're also going to look at the limb of the sun.
Yes. Okay. So maybe keep coming in chat. There's 20 of you, or in the questions box. I'm sorry. Primarily we use Zoom, so sometimes in GoToWebinar I forget that it's questions. So in the questions, please keep letting us know where you're coming from or where you're calling in from, and also put in any questions. So until we start the scan, we would love to be interactive with you. I think now we'll probably go to looking at some of our other slides. So we'll move from this and share a little bit more about the science.
Yes, so we'll give a little bit of background information on what is an eclipse, what you can expect to see during an eclipse, and also the kind of science that we can do during the eclipse itself, and specifically what science we'll be doing with GAVRT. So let me just share my screen here. Separate button.
Yep.
Let's see.
I'm still seeing. Let me go back and see if I need to. Oh, we have some questions. Go back. Okay, now, I'm gonna, there we go. Yeah.
All right. So I think now we should be seeing my presentation. Looks like it's not in presenter mode though. That's fun.
And while we get started, Sandy had a good question for us. So what is the story of GAVRT and how did it originate? I can take that question. That is a really fun story. So we call this kind of our family story. So the way that, so our motto of GAVRT is and always has been real science, real education. And that comes from the way that GAVRT all started. So the Lewis Center founder, Rick Piercy, was a kindergarten teacher, and then he was a vice principal and principal. And he had an idea that students would do better if they were really involved in hands-on science. And so he started a Young Astronauts Club after school. And there was a big observing night where everybody had a night under the stars, and he was very surprised. You know, he thought, oh gosh, I don't know, nobody's probably going to come out. It's really cold in the high desert, and hundreds of people came out. And so it was just like, it kicked off this huge groundswell of just the community coming around space science and hands-on science. And this was back in the early 90s. And so that started to grow. And then Rick heard that NASA was decommissioning a radio telescope out at Goldstone. And he said, I want to expand my program. And so I think that would be a great idea. So he was an amazing man, but he decided to just pick up the phone and call NASA. And he said, you know, hey, this is who I am. I run this project, an astronauts project. I'd really love to have the telescope for use with our students. And the way the story goes is they just really appreciated his chutzpah. And so they forwarded his call to Dr. Mike Klein. And so just as much as Rick was beloved here at the Lewis Center and throughout the entire high desert community, so was Dr. Mike Klein throughout JPL and NASA. And as the story goes, the two of them hit it off right from the very beginning. And so Mike loved Rick's idea and wanted to find a way to make that work. Also, Rick didn't really know what a radio telescope was, so he really thought that he could go pick it up out at Goldstone in his truck and just bring it on up to campus. Well, we know, and Marin will definitely show you, or like the screen shows, I'm pretty sure there's some buildings there for reference of the scale of the radio telescope. So for surely it did not fit in the back of Mr. Piercy's truck. But even back in the mid-90s, found a way to remotely connect to the antenna, and the rest is history. So between the two of them, they found it very important that anything that's done with the GAVRT project, it contributes to the scientific body of knowledge, and it also contributes to real education process for the participants. And so we've stayed true to that all the way since we were an official project in 1997. And so every campaign that we'll talk about that we are currently doing fits the mission of both of the GAVRT founding fathers, Rick Piercy and Mike Klein. So we love that story just because it's just born out of the minds and collaboration of two great men, and we all feel very fortunate to continue their work. So, yeah, it's a GAVRT story.
It's a cool one.
Yeah. In our training, we have a little slide I need to share with you with the telescope, and then a little red truck when we tell this story. So you can kind of see the scale, like, oops, that would not fit.
Yes, so yeah. The GAVRT telescope's 34 meters, and 34 meters is really big.
It's really big. Yeah, so that would not fit. But. All right, so let's talk about what we're going to be doing today, and I will continue to see if we have other questions.
Yeah, so I can just give a little bit of a background on just in general, what is an eclipse? Why are they so special here on Earth? And then we can talk about exactly what science we're doing with the eclipse today.
Yes.
So an eclipse is just a general term for when one astrophysical body passes in front of another astrophysical body. And that is happening all the time in the solar system, in the galaxy, in the universe. And the image I'm showing here is actually an eclipse with Saturn. So this image was taken by the Cassini spacecraft as it passed into the shadow of Saturn. So the sun is fully hidden behind Saturn in this image, in this eclipse image, but you can tell that it's back there because it's really nicely backlighting the rings and atmosphere around Saturn here. Fun fact, we're all in this image. We're actually right there. That little blue dot isn't dust on your screen. It's actually the Earth, which is really neat.
That is cool.
So the coolest kind of eclipse, in my unbiased opinion, are the ones that you can see from Earth, and specifically solar eclipses. So people might be more familiar with lunar eclipses when the moon passes into the Earth's shadow, and you get a really nice red moon that's visible from the entire side of the Earth that's facing the moon during a lunar eclipse. But solar eclipses are even cooler. And they're what I like to call a cosmic coincidence, because I really like alliteration, but also because it makes it sound exciting.
Yes.
But it is exciting because there's a really nice thing about our system, that the size of the moon is about 400 times smaller than the size of the sun. But because the sun is about 400 times further away, thanks to geometry, what that means is that when the moon passes in front of the sun, it almost perfectly covers the entire solar disk. So you get what I'm showing in this cool little graphic here from NASA. You get a total solar eclipse where the moon fully obscures the disk of the sun. And if you are experiencing a total solar eclipse, and if you're in the path of totality, what you will see during the moments of totality is the atmosphere of the sun, the corona that I talked about earlier. It's this plasma that surrounds the sun that's millions of degrees Kelvin, If you see a total solar eclipse and you look at the corona, it's the hottest thing that you'll ever see, the hottest thing you'll ever lay eyes on. It's this very beautiful, tenuous atmosphere that is about as bright as the full moon during a total solar eclipse, that you can't see at any other time because the disk of the sun is so bright. So you can only see it when it's being fully obscured during the eclipse. And it's even more of a cosmic coincidence, not just that the sun happens to be the same size as the moon in the sky, but it's also a coincidence that we can see it at the specific time on Earth. So the moon actually used to be much closer to the Earth when it first formed than it is today. So if you were viewing a solar eclipse a few billion years ago, you would always see a total solar eclipse. You'd never see a partial eclipse or an annular eclipse. And the moon would be obscuring the corona, so you wouldn't get to see any of these cool coronal features that we're talking about. And about 500 million years from now, since the sun used to be closer to us in the past, it's also getting further away. Turns out about 1.5 inches in a year. It's getting, every year it moves about 1.5 inches away, the same rate as your fingernails grow. So that means that in 500 million years from now, the moon will be so much smaller enough in the sky that it will no longer fully cover the disk of the sun. So we'll never get total solar eclipses anymore. We'll only ever get annular eclipses. And an annular eclipse is,
I was going to say, should we talk about the difference?
Yeah, let's go into that. So a total solar eclipse is when the moon fully obscures the disk of the sun, like I said, and you get two kinds of shadows on the surface of the Earth. So you'll get an umbral shadow, which is the path of totality, and you'll get a penumbral shadow, where basically you're still in the shadow of the moon, but the moon's not fully obscuring the sun, so you'll still get some daylight coming through. Umbra is just the Latin word for shadow, and penumbra is the Latin word for partial shadow. So what's happening during an annular eclipse is the moon is actually a little bit further away from us in its orbit. So the moon's orbit isn't perfectly circular. It's actually a little bit squished. It's a little bit elliptical. So when it happens to pass between the Earth and the sun, when it's in that furthest part of its orbit, what happens is that umbral shadow focuses to a point that's not on the surface of the Earth. It's actually a little bit further from the surface of the Earth. So there will be only the penumbral and something called an antumbral shadow. And what that means is if you're in the path of the antumbral shadow, you'll be in the path not of totality, but the path of annularity. And what you'll see in that path of annularity is what we call the ring of fire. Let's see, I've got an image of that here. It'll look something like this. So today, if you're in the path of annularity and you go and look at the sun at the right time, what you'll see is something like this, which we call the ring of fire. So you can see that the disk of the moon there, it's not fully covering the entire surface of the sun because it's further away from us in its orbit, and you get just the outer ring of the sun, and it's quite cool. So yeah, that's what an annular solar eclipse is. So there will also actually be a total solar eclipse in April of 2024, so coming up, not too long after today's eclipse, and that will be a total solar eclipse. So if you are in the path of totality or anywhere near the path of totality, I highly recommend that you go into the path of totality to view the solar eclipse. Yes. It'll be a completely amazing experience. Yeah. And Lisa, you've seen a total
I have. My family and I had the awesome first time experience of seeing the total eclipse the last time in 2017. And Marin and I were talking about it before, and it's just like an amazing experience. I would be interested if any of you have also had that experience. It's just like nothing you can describe. And I was laughing saying that my youngest daughter, who's an adult now, but she was still in high school then, was complaining because we got up very early. Well, we got up at like 11 p.m., started hiking at about 11 p.m. and hiked to Boulder Peak in Idaho, and which was in the path of totality, but to view it on top of a mountain just added an extra element of being cool. And so we hiked all through the night until the time of the eclipse, and she was complaining the whole time. And then when it happened, she was just like, her reaction was probably one of the coolest things ever. She was just like, oh my gosh, like, but you know, she was just completely overwhelmed. And so it was something I will always cherish. So oh, yay, Bo. Nice to see you, Bo, from our summer 2015 training. Yes,
Nice.
it's good to see you. Has anybody seen a total eclipse? Or is maybe planning to get into the path of totality in April?
Yeah, I'm planning that.
Yes.
I've never seen a total solar eclipse. I've only seen a partial eclipse,
Yeah.
so I'll be very excited to
Yeah.
see this next one that's coming up.
I need to figure out a way to do it because it's just such a cool, like, I think that once you've experienced it, you just want to keep doing it over and over again.
Yeah, like I've heard people say that they were moved to tears when they saw the total solar eclipse.
Oh,
It was
for
something
sure.
they'll never forget.
Yeah, yeah. I think too, for us, one of the cool experiences was being there. So being on the top of Bora Peak, there were people who had come from all over the world.
Wow.
To also do that hike and to see it from that vantage point. And it was just really neat to see, you know, fathers and sons from, you know, Europe, or just, I don't know, there was just a whole big group. And it was funny, like all the people up there, we just kind of bonded, and we're sharing different viewing apparatus and different things and stories. It was just something so special.
Yeah.
So
wow.
Love to hear you guys' stories. Oh yeah, Sandy has a great question. Do we always need to wear eclipse glasses when we're viewing an eclipse?
I love that question,
Yes.
Sandy. That's a good question. So during today's annular eclipse, yes, you always need to wear glasses. Whenever you look at the sun, you can only do it with something like this, eclipse glasses like this. And these are
I can see.
Have a standard. I know, yeah. Once you put them on, you know they're working because you can't see anything. They block out more than 99.9% of the sunlight at both optical frequencies, which is what you're used to seeing with, also at infrared frequencies, and also at UV frequencies. So that's just to protect your eyes from damage. So usually, if you were to go and look out at the sun on a normal day, if you were to accidentally glance at it, it would be painful because it hurts your eyes. But it's especially dangerous to look at the sun during an eclipse because it gets darker, and so your eyes dilate. So your eyes are bigger, so they're letting in more photons, and so you're at extra risk of damaging your retina. So yes, always look at the sun with your eclipse glasses. Make sure that they are an ISO 12312-2 standard, and make sure that there's no holes or tears in the actual glasses before you put them on to look at the sun.
What could we do if we don't have eclipse glasses?
That's a great question. So if you don't have eclipse glasses, you can still view the eclipse from where you are. One really cool way to do that is, rather than looking at the sun, is to look at shadows. So if you were to look at maybe sunlight filtering through the leaves of a tree, what you would see is in those shadows, every shadow would be a mini version of the eclipse.
Yes.
You can also make your own pinhole camera. So you would set up a box, make a pinhole in it, and then have a separate area for viewing with your eyes. And you would turn your back to the sun, the sunlight would come through your pinhole, and what you would see when you looked through would be the shadow of the eclipse that's happening. If you have internet connectivity, you can go to nasa.gov. They'll be live streaming the eclipse both today and in April as well. There'll be lots of opportunities for viewing the eclipse.
And there's also all kinds of ways to make pinhole cameras online. So instructions of how to do that with just general supplies that you have at home.
Yes.
So I know a lot of times our kiddos.
Yeah, we'll make one on the fly for you right now.
Yeah, Erica. So our one of our operators, Erica, is just on this side of the camera. Do you want to show, Erica? Yeah, I'm going to switch out, and Erica's going to show you how to make one with just paper and pencil. All right, switch.
Good morning, everyone. So one of the things that I've done before looking at an eclipse is you just take a normal piece of paper. Pretty much everybody has these at home. Piece of pencil or something to make a nice round hole. You just want to stick it right through your paper. Then you can hold it up to where the sun is going to shine through that hole, and the shadow on the ground is what you're going to look at. So that's going to show you the little bite that's going to get taken out of the sun's circle as you're watching the eclipse, but don't look at the sun. Just look at the ground.
Yes. Oh, that's super cool. Yeah.
So yeah, it's a simple, easy, quick way to do it.
That's all you need.
Or I've also seen it done with a colander if you're at home.
Oh, that's a good idea.
You can just use a colander, and then you get a bunch of little circles on the ground.
Yeah, a bunch of little mini eclipses.
Little mini ones.
I do want to note, though, that if you are viewing a total solar eclipse and you're in the path of totality, during totality, you should take your glasses off, because You won't see the corona if you have your eclipse glasses on and you want to see the corona. You'll only have a few minutes to look at that tenuous atmosphere that I described before, the atmosphere of the sun, that tenuous plasma. And it's supposed to be, I've heard, very beautiful to view in person. So during totality, you do want to take your eclipse glasses on, but you want to make sure that you have your eclipse glasses back on before totality ends. Very important to do that.
Looking at our little map on the screen here, it looks like, isn't that San Antonio, Texas right there in the crosshairs of both eclipses?
It is, yeah. San Antonio is really special. So usually on average, a single geographic location on Earth will only see a total solar eclipse every, on average, 350 years, I think. So it's really special that San Antonio is seeing 2 eclipses within 1 year. That's very awesome. And I know one of our GAVRT scientists, Steve Levin, is there, I think right now, viewing the eclipse. Steve, if you're watching, hi. I hope you're having a great time. Can't wait to see those pictures. So yeah, San Antonio is a great place to go. Also, I think one of the things you need to think about when you're planning eclipse viewing is weather. So if there's clouds, you won't be able to see the eclipse. So going somewhere where there's really good weather is important. And San Antonio has a great weather forecast for today and also in April. So if you are looking to view the eclipse, then I highly recommend that you go to Texas. It's one of the good places to view.
So the next, the total solar eclipse coming up is April 8th of 2024, correct?
That's right, yeah. And it'll start, it'll cross first into Mexico, and then go up into the United States via Texas, and then out via the Northeast, and kind of up into Canada there.
Nice.
So these tracks, the orange track here, I think you can see my cursor. Yeah, awesome. So that orange track is the track of the annular eclipse that's happening today. And then this purple track is the path of the total solar eclipse that's happening in April. So yeah, let's see what else I've got here. So we showed the ring of fire already for the annular solar eclipse that's happening today. Here's a sort of representative image of what you can expect if you are viewing the total solar eclipse in the path of totality during totality. So this white gas plasma, I should call it, that you're seeing here, that's the corona that I've been describing, the outer atmosphere of the sun. Corona is Latin for crown. And you can see why it looks like a nice, beautiful crown on the disk of the sun. And there's a lot of structure that you can see in this corona, even in this image. You can see sort of what look like lines or streamers coming off the surface of the sun, maybe even some structures that might look like loops that are connected. And that's all descriptive of the magnetic field of the sun. So features in the corona are tied to the magnetic field structure of the sun. Now is a really exciting time to view the sun, both from a scientific perspective and if you're trying to view the solar eclipse, because the sun is going into an active period. So the sun has an 11-year activity cycle where it goes from being very, what we call magnetically quiet, not very magnetically active, very quiet, where it doesn't have very many features. Sunspots, that's what I was looking for earlier. Sunspots, and not very many active regions, not a lot of flares or coronal mass ejections. And it's now entering a period of peak activity. It's entering the peak of its solar cycle, which will happen in 2025 approximately. And it's producing a lot of those things. So a lot of sunspots, a lot of active regions, a lot of flares, and a lot of coronal mass ejections. Where flares are bursts of energy on the surface of the sun, where you're releasing a lot of electromagnetic radiation. And coronal mass ejections are sort of like the high energy particle counterpart to that. So you have an explosion on the sun that's releasing millions, billions of tons of mass out into the corona and out into space. We call those coronal mass ejections, and they happen a lot during periods of peak activity.
I always hear those referred to as CMEs.
Yes.
I had to make the connection there between CME and coronal mass ejections, but I knew what people were talking about.
Yes,
so.
yeah. We shorthand refer to those guys as CMEs.
Yes.
And the sun's been producing a lot of them, and it's going to produce even more as we go into the peak of that activity cycle.
Exciting. Good times.
So we were talking about this a little bit already, but what it's like to be in the path of the total solar eclipse, it's so much more than just what you see visually. There's so many senses that are triggered. You feel cold because the shadow of the moon is preventing sunlight from reaching you, birds and other creatures will start thinking that it's nighttime. So birds might be getting ready for bed. So it's a really cool experience that we highly recommend.
Okay, so I think we're going to go ahead and start our first scan. So Ryan's going to switch over, and then they are not mic'd up over there though. So if you want to kind of talk about what we're seeing, so.
Okay.
Yeah, and I'll have them, you and I can play off the brand together.
Okay, yeah, that sounds good. If you want to come over here and switch with me, that'd be good too.
Oh, no, you're gonna say that.
And then Erica, do you want to look on my computer on the questions? Because we might have some. And then I'm just not
I
seeing it.
haven't seen anything since
Okay.
the Eclipse classes were doing.
Okay.
All right, so we're back on our control screen here. As our operator, Miss Nancy over there, and our scientist Velu are getting ready to take our first scan of the sun.
Yeah, and I was just gonna give a little background. So we were waiting for the sun to rise. So the sun rose at 6:53 this morning in our view, but we have to wait until the sun has come up at least 7 degrees above the horizon before we can track. So we are currently at, if you look at our screen, our elevation is 8.768. So right now what we're doing is a raster scan of the sun in an effort to verify what we expect in terms of all the active regions that are going on. And so slowly we'll get an image of the sun here as we go.
This is exciting. I can see stuff up here.
Yeah, right. Big shout out to lots of people, especially Goldstone and the Venus personnel, for just a Herculean effort to get us online. They've been working on our receiver and everything came together just in time. So big shout out to the Venus crew.
Yeah, experiments like this take a huge team of people with so much effort. All of the engineers and staff on site at the antenna, people like Ryan and Nancy here that are running the telescope and doing all of our tests. Dr. Velu over there, our scientist, GAVRT, who's telling us where we need to point, which active regions we're targeting, and doing some of our calibrations as well. So yeah, huge thanks to everyone for making this happen.
You guys explain what a raster scan is.
I'll let you take that one, Ryan.
So many years ago when we had CRT TVs, so cathode ray tube.
I remember those.
Yeah, right? It's a lot nicer now with a very skinny, sorry, I'm just looking at that raster and thinking I need to go fix something. Old school days, your TV would be drawn one line at a time, really fast, where it was imperceptible to the viewer. And so that was called a raster pattern. And so that's exactly what we do with our telescope when we're taking an image of the sun. We go line by line and basically do a map, taking data points every 20 milligrees depending on what frequency we're using. So I can see right now we're using 8.4 gigahertz for the prime frequency for our observation. And so just like our old TVs is exactly the scanning pattern that we do with our antenna.
And radio telescopes are unique in that they're not like what you were used to with an optical telescope or like with the camera on your phone, where you have a CCD with Brian's gonna go fix things. Like on your phone or your camera, digital camera, where you have a CCD and you can expose and you're seeing a large field of view. And you have, in addition to that large field of view, you have individual pixels that represent individual discrete locations on the sky or in whatever you're taking a picture of. With a radio telescope, we have just basically a single large pixel. So what Ryan was describing with the raster map is we're basically building up those pixels over time by pointing the telescope at a specific location on the surface of the sun in this case, collecting some data, then moving the telescope, collecting more data, etc. And with that observing strategy, we can build up a picture of the sun, and that's that raster map that he was talking about. So I see it's been cleared off the screen.
We're firing up another one right now.
Sounds like we're about to take another one. Oh, this one looks good. It's like something's happening here. We'll see.
I was just gonna say something about integration times. I'm not sure
Yes.
if you want to talk
No,
about.
no,
So
right.
our sampling rate that we're using right now, you can see in the boresight window, it says 250 millisecond, 250 milliseconds per sample. So we get 4 data points per second. And so when we updated it on Xant, the raster didn't quite get the message. And so we just had to send another command to it telling it that expect data points every 4 times per second. The default when we bring up the system is 500 milliseconds. And so that's why I was kind of missing a line. So one line and then it missed it because the XPlot where the raster is mapped was expecting one thing, but the antenna was doing something different. So,
Antenna doesn't always do what it's told.
yeah, we're doing a very small raster scan, really quick, just to verify that everything's good. We don't have a lot of time before we're going to go to our first active region. So at 14:55, so we have about 10 more minutes before we go to the active region. Did you already talk about what science are we getting when we do that stare?
Yeah, that's a good segue. So maybe I can take over the screen again.
Yeah, let me make you presenter again.
Also, they said had a question, is Goldstone and location?
Oh, that's a good one.
Oh.
Yeah, so the Deep Space Network is comprised of 3 sites. We are fortunate enough that 67 miles north of us here in Apple Valley, California, on the Fort Irwin military base is Goldstone, California, where the United States Deep Space Network site is. There's also one in Canberra, Australia, and one in Madrid, Spain. The idea being that they're spaced roughly every 120 degrees on the globe. That way you get that full 360 degrees of observation time when our spacecraft are out there. Australia picks up a bit of the southern hemisphere, and then us in Madrid get the northern hemisphere.
Nice, yeah. While Ryan was talking there, I pulled up a map that shows where those 3 deep space communications complex or DSN complexes are located.
Yeah, perfect.
So yeah, we're here at this one right next to Goldstone.
Yep.
And the stations are very conveniently spaced in longitude on the Earth so that any spacecraft wanting to communicate or get communications from Earth will always have a DSN station in reach. Since this is primarily how NASA communicates with all of its spacecraft.
Yep.
And we're lucky in that one of the DSN dishes is now retired and used by us.
Yes, yes. Yeah, we were originally given Deep Space Station, so DSS 12, which was used many, many moons ago to observe the Echo weather balloons. So our original GAVRT antenna is at the Echo station. Right now we're using DSS 28, which is at Gemini. It is, there's a pair, they're twins, about 100 yards apart, hence Gemini, the twins. So DSS 27, which is now fully decommissioned, and then DSS 28 is our active antenna. And then we also have the opportunity to run on the research and development antenna, DSS 13, which is at the Venus site.
Nice. All right, I'll go back to that slide I was showing here.
I'm gonna tap Lisa in so I can go make sure all is well. I'll be back.
Good. Ryan's gonna go make sure that our observations are done. But I'll talk a little bit about what we're trying to observe. So if you're just joining us, I'm talking now, I'm showing a slide about the observations that we'll be taking today, that we just started taking with our GAVRT telescope on the sun. What we're going to be doing is targeting what are called active regions. So those are, we can think of them like hot spots in the corona, in the atmosphere of the sun, above sunspots that we see on the photosphere. And those active regions are basically regions where the magnetic field is doing something exciting. And so what we want to do during the eclipse is take advantage of the moon's limb passing over those active regions. And what that gets us is really high angular resolution on those active regions. And that's what this movie is showing. So this was a movie that was made by Dr. Velu, who's one of our scientists with GAVRT. I'm sitting over there at the control panel. Yes, PI of Solar Patrol GAVRT. And so what he's showing in this image is the surface of the sun, which is this great image in the back. This circle represents the antenna beam of our GAVRT antenna. So that's that single pixel I was talking about, rather than having a camera with multiple pixels like your megapixel, whatever, iPhone, Android camera. With our GAVRT dish, we have just one single large pixel. And so normally when we measure the flux inside that aperture here, this black circle, we're just summing up everything that's in there. But what happens when the moon's limb passes in front of that aperture is we get really high angular resolution corresponding to the moon's limb passing in front of structures in that active region. So this plot that is shown on the bottom here is showing basically the amount of power we're collecting inside that aperture, inside this black circle, as a function of time. And basically the derivative of this curve, how this curve changes as a function of time, is giving us information about how structure that's inside that aperture, and basically how things are changing spatially inside that active region.
That's why an eclipse is such an exciting time for us in GAVRT.
Yes.
Because we can collect data in a way that we can't in normal times.
Exactly, yes. We're getting really high angular resolution that's independent of frequency. So normally angular resolution is directly correlated with the frequency that you're observing at. So if you're at really low frequencies, in this case maybe 3 gigahertz, you get even worse angular resolution. So this aperture here, this black circle, would be even bigger. But because we're taking advantage of the moon's limb crossing in front of the sun, we're kind of getting really high angular resolution at all of our observing frequencies for free. So it's a really exciting time to observe.
And on our GAVRT site, I didn't post this, but maybe I'll go and put the link in there. We've published papers from the last eclipse when we gathered GAVRT data.
Yes.
And so that's the intent here as well. So as the data come in from today, we'll be able to hopefully invite all of you to participate in some analysis of that data. And then of course we plan to publish those results as well.
Yes, yeah, definitely.
So that's an exciting part. Okay, what questions do you guys have? Thank you for sticking with us. Some of you have been on the whole time. Some of you have been joining us, you know, as we've gone in and talked. We do want today to be very interactive, so please ask us any questions that you have. Let us know where you're calling, joining in from, and oh, Sandy has a good question. And any experience that you've had with the GAVRT project. We love GAVRT stories or ways that you've maybe interfaced. We know that Bo is a trained GAVRT teacher who's joined us. We have, I think some of our Lewis Center board members are still on. Marin's mom is still hanging in. So of course, we just want to be very interactive. Also, I would love to know what time it is where you are. So it's still pretty early in the morning here in California, 8 minutes before 8 a.m. So Sandy would like to know what happens during a typical GAVRT school session. So I could probably take that. So if you are not already a GAVRT trained teacher or facilitator, it's really easy to do that, to join us. And in fact, you really need no experience at all, because our operators, Erica or Nancy, will be able to guide you every step of the way. So what's really cool about GAVRT, so Marin is placed on the screen so you can see what are some of the benefits of running a session. So it doesn't have to be just in a school. We can really adapt GAVRT to meet whatever needs you have. So maybe it's a before or after school program. I know especially in the States that there are a lot of COVID funds for extended learning. And so a lot of schools and informal education institutions are grappling with how to extend the school day and provide really meaningful experiences, especially those related to STEM. So GAVRT is great because it's completely free to you, and you don't have to have a lot of experience. So, but here are some of the benefits, and I'll tell you how you can do it. So the great thing is that you get to work with professional scientists like Dr. Anderson here, and Dr. Bailu, and Dr. Levin, and all of our amazing scientists who are part of the GAVRT project. So you get to do that, and your students or participants are able to have one-on-one conversations with them. That is really great. But also you're working with your participants to help them uncover new knowledge about the universe, and that's pretty cool. Actually, Marin and I were just having a conversation about why she became a radio astronomer. And that was one of the things that you said, that it was a more complex way to learn about the universe.
Yeah.
And so that's one of the main goals of GAVRT, and something that you could bring to your students or participants. And then probably one of the most unique things is that you actually get to control the 34-meter radio telescope that belongs to NASA. So NASA is allowing you, through our operators and through this project, to use a tool that would typically not be available to somebody who's a citizen scientist or a student. So that's probably one of the really neatest, aspects of our program. And then, like I said, you receive support from the Lewis Center and JPL every step of the way. So Nancy will do your onboarding training. I think, do we have, what's the next slide that we have? It might show. No, go yeah, go to this one. So just if you just were to use the mc@lcer.org, you could email us if you wanted to receive the training. So that MC stands for Mission Control at Lewis Center for Educational Research. So if you email that email, that's a general email that goes to the entire GAVRT team, and we could get you set up with a quick tutorial, and then we'd be able to launch into a session. And then during the session, it is going to be, we're going to kind of walk you through what a session looks like today as we're completing the raster scan. And then we'll also talk to you about some of the other opportunities that we have besides solar patrol. So we have 3 other campaigns that you could do too, just depending on what fits into your needs at the time. So we can adapt it. So once we hear from you, we can say, hey, is this just a one-time event that you want to do? Do you want us to join you? Maybe you're doing a space week at your museum or at your school. We would love to jump in and plan with you and partner with you. Maybe you're a classroom teacher and you have a unit that comes up once a year that this would be a good fit for. We'd love to do that. Or maybe just even during this really cool event like an Eclipse. So we can adapt it to anything from like once a week and you want to regularly run sessions, or once a year, or just once in a lifetime offering that you give at your organization. So again, just email us at mc@lcer.org, and we'll be able to talk to you and see what your specific needs are. And also the time of the session varies depending on the campaign that you run. And so we could also adapt that to what your block of time looks like. And, oh, okay. So Thark says that this is the first time that the timing of the session is in my favor because it's 8:30 p.m. in India. Usually you have to wake up around 4 a.m. So that is really good feedback for us. We do have a lot of participants joining from India. And so we are working on the timing. So as we develop more just open citizen science sessions, especially as we look at analyzing the data that we collect from today, we will be mindful of that and maybe even offer a couple of times so that depending on where you are in the world, it works out better for you. So thank you for getting up for us at 4 a.m. And I'm glad that, 8:30 p.m. seems like a little bit more reasonable of a time. So
we need our own follow the sun model.
Yes, we do.
Provide a session for each part of the world.
Exactly.
So that no matter where you are, it'll work for you and you don't have to get up at 4 a.m.
Exactly. Although Erica and Nancy also often get up, depending on the group that they're running with. They may be here at 4 a.m. California time or any time that they can do observations. Okay, Bo has a question. Are there heat problems with focus on the sun for an extended period? It seems that focusing sunlight on a single point for a long period would heat the receiving electronics to an extreme.
Oh, that's a cool question.
That's a really good question, Bo. That's why you're a GAVRT teacher.
Yeah, so usually you have, there's a couple things that you can do to mitigate what you're describing. So there's a solar filter that we can put in front of the receiver to attenuate a lot of the radio emission that we are receiving, since it's a lot more power than the telescope's used to getting when it's pointing at usually an astrophysical object or a spacecraft. Suddenly you're pointing at the sun and you're getting a ton of power at radio frequencies. So you can have that solar filter there. And we also have attenuators to attenuate the signal from the sun.
Interestingly enough, though, I don't think we're using our solar filter now, right?
That's
It was
right, yeah. So
distorting the,
we were having some problems using the
Mhm.
solar filter, so we ditched the solar filter and we're just working with the attenuators. So they're enough right now to prevent sort of the damage that you're talking about. But a lot of radio facilities have to have just kind of what you're describing, attenuators in place, something special to basically protect the telescope, the electronics from the sun. So for example, the Very Large Array in New Mexico, or the VLA, which is a radio telescope, a US radio telescope operated by the National Radio Astronomy Observatory, NRAO. They have a special set of observing configurations for when people want to view the sun with the VLA.
yeah. Another really good question. What does follow the sun mean? Yeah, sometimes we throw these NASA terms out.
Yes.
So maybe go back to do you want to go to the DSN?
Yeah,
Maybe that's the term.
that sounds like a Sandy question. Here we go. Yeah, so the DSN, or the Deep Space Network, which again is how NASA communicates with all of its spacecraft, and not just NASA spacecraft, but sometimes NASA allows other space agencies to communicate with their spacecraft using the DSN. They've started this I guess, observing format, pattern, called Follow the Sun, where basically the staff at a given DSN complex, so either Goldstone in California, Madrid in Spain, or Canberra in Australia, will be in charge of communications at any given complex when it's their some daylight hours. So the operators at each complex will go into work during their daylight hours, wherever they are, and be in control of communications for all the
Kind of
complexes.
pass it to the next complex as the sun moves and they're able to observe, right?
Exactly, yes, yeah. And again, the complexes are spaced out in longitude on the Earth so that there's always a complex available for a given spacecraft, no matter where it is in space.
Yeah. So, and we're really lucky that our organization just happened to be located really close to Goldstone here in the desert of California, and that gave us an opportunity to launch this project. Even though some of you, we can do it from all over the world, right? Just like we are doing now, but it's really neat that we have that proximity to Goldstone. So it's made it good for us. And we've done that in GAVRT too, right? So like we participate while we're able to view, and then we also have worked with education projects at the other complexes and done some of that work over the years too. So that we do our own little citizen science, follow the sun.
Yes.
Okay. Well, how are things looking over there, you guys?
It's going.
It's going.
We are currently working on some pointing offsets and trying to make sure we have the active regions within the beam.
Okay.
So we are
Calibrating and
working on the fly to update pointing models and expectations for where the active regions are and the sun. So we're doing some quick calculations real fast.
Dr. Belu is on a mission right now on camera. Our principal investigator is very much, yes. So I think that that's kind of a neat thing too. It's just like the tool that we're using, right? And it's pretty massive, and we've had to do a lot of work, I think, to make sure that it was ready to collect this data. And it's a really special thing that we get to work with, but it still requires maintenance and tweaking and those kinds of things in order to make sure that the data that we get is good. So even in real time.
About 4 minutes until the sun starts passing.
That's why I sense from our observing team a shift.
This is how science goes, though. This is how observing goes. You're always frantically making sure that things are working at the last minute. Nothing ever works right the first time. That's always been my experience.
Yes.
No matter what telescope I was using.
Yeah, and I think that that's the really cool thing about GAVRT is that it has given over the years an opportunity for our students and participants to view that, right? So like I remember Dr. Levin is part of the, I wish you guys, I almost want to switch the angle of the camera because to feel the room and how all of this is working is really exciting. But to have our students in the Juno orbit insertion, right? And so for the Juno spacecraft, we were able to be there with the science team and to just feel that anticipation. And then when it all went off without a hitch, it was very exciting. And I hope that we have similar success today, because like Marin was saying, we've been gearing up for this event for a really long time, for several months now. And so this is such a great opportunity. We don't want to miss it, and make sure that we get all the data that we can.
Yeah.
As we shared, these eclipses don't come all the time.
Yes.
So
But we have 3 hours. The eclipse
We
is
have
gonna
3
last
hours.
for a while, so
Yes.
we got some time to figure it out.
yep,
And we also have next year too. That we'll also be observing during the total solar eclipse. It'll still be a partial from here, from California and Goldstone.
yep. And I think too, like, even if it doesn't all go off without a hitch, you learn no matter what.
Exactly.
That's the other thing about real science, that a lot of times in the classroom, in a formal classroom setting, we kind of get all the parameters figured out.
Mhm.
And so it's a little bit staged, right? And so there's always a right answer. There's a way to solve the problem. And in the real world, it's not always that way. We don't always have the answers. We don't know. A lot of times, you know, Belu or Marin or other scientists we work with don't have that answer, and we collectively are working together to figure it out in real time.
Yes.
Even if you have a lot of preparation. And so I think that that's one of the great things that GAVRT offers, is that perspective of what real science looks like. It's not always clean.
Right.
And when you're adding to the body of knowledge, nobody has the answer yet. So it's all new. And that can be scary, frustrating, but also deeply rewarding.
Definitely. Wow. I couldn't put it any better, Lisa.
Much better than a worksheet, as the kids would say.
Yeah, if we already had the answer, we wouldn't be doing it. So
Yeah, yeah.
all the excitement comes from
Mhm.
trying to figure out how to get the answer and how to make things work.
Yeah. So they're just over there, and so that's why I'm kind of looking. How are things going over there, guys?
They're good. Hey, I wanted to share a
Can you wanna
couple,
switch?
couple
Let's switch.
resources real fast.
Okay.
Helioviewer.org is a great resource for seeing the active regions, and then solarmonitor.org as well. So right now, and if you go to those, you'll see some NOAA designations for the active regions. So right on the limb of the sun in the kind of upper right quadrant, we're looking at AR 13455. Yes, exactly where Marin has her mouse. Yeah, that spot right there. And so we were updating some offsets, and I believe that we are on that point, and at 1508. The moon should pass. So what we'll see in our X-plot is we have total power coming into the antenna. And so as the moon goes over that, we should see that decrease dramatically from sun to moon. So I think we're good right now.
Awesome.
But again, helioviewer.org and solarmonitor.org are great places to follow along. And I will give you a list real fast of all the active regions that we're shooting for today. So we are starting with AR 136455 over on that west limb of the sun. After that, we'll go to 13462, then 13465, 13462 again, and then 13465. So we catch it as the moon goes over, and then when it goes back off of the source, or of the active region, sorry. So I'll put that in a question so that everybody can kind of see our sequence of events and the active regions that we're looking for today.
Very cool. Ryan, do you know how to make the HelioViewer turn on the active region names?
Yeah, over on data source. And so this was doing this to me earlier. It's usually you just click on the active region, but I'm not sure why it's not showing that. If you go back in time one day, it should pop up.
Oh, okay.
Let's see. Yeah, you just hit the back arrow on the 1 day interval. There we go. See, I don't know why it's.
There we go.
Yeah.
Yeah, so it doesn't show us 136455 right now because it's kind of gone over the limb, but Dr. Bailey believes that we should still be able to get some good data off of it.
Nice.
Yeah. And so, yeah, you can see that sequence. So then 13462 is the next one that we'll go for. Yep.
Right here.
Yep, right there. And then we'll go to 13465.
Right there.
Yep. So kind of in a line, a straight line-ish for us. And those, all three of those active regions, as well as I think all of them for today, except for that nice one that's starting to form over on the east limb of the sun. We'll be able to get good coverage today.
Will 13464 there, will we catch that in the beam?
So that was a good question that we were talking about. Do you want to talk about frequencies, beam size, and I think Bailey said they're about, Bailey, was it about 15 milligrees or 30 milligrees between? Bailey was
He's deep in
rapid thought. Yeah.
Working over there.
Yeah, so that's a good question. That was my concern as well, is that they're so close in proximity that we might not be able to resolve them as well.
Right, yeah.
Yeah, we're gonna have to make sure the pointing is top notch for that region to make sure that we're not getting the other one as well.
Yes,
So,
yeah, so I can
yeah.
talk a little bit
Oh,
about
there you
beam
go.
size.
Beautiful graphic.
Yeah, so this was that movie made by Dr. Belu that I was showing earlier. So the beam size that we're talking about, that's represented by this black circle here. That's basically telling you your angular resolution of your telescope. I was referring to it earlier as like your single pixel on the sky that your radio telescope is giving you. And so the size of that single pixel is given by basically your observing wavelength divided by the aperture of your telescope. So the aperture of our telescope is 34 meters. And our observing wavelength is going, so I'm going to switch here. I'm going to switch now to talking about frequencies.
Yeah.
So wavelengths and frequencies are the same. They're just related by the speed of light. So our lowest frequency is about 3 gigahertz.
Yeah, 3.5 for today's observations.
Okay, perfect.
Yeah.
And then our highest frequency is at 12?
14.
14. Okay.
14 gigahertz.
Going up to 14. So the beam size at 3 gigahertz should be about, it's big. It's big. It's about 3 times,
small.
Yeah, 3 times larger than the beam size. Did I do that math right? 3 and a quarter times larger than.
Sounds right. I'm not gonna call you on it.
3 times larger than the beam size of 14 gigahertz. So if this were the 3 gigahertz beam size, then 14 would be a smaller circle on the sky here. So that's what Ryan and I are talking about. So at 3 gigahertz, where we have a much larger beam, it's potentially the case that we would capture multiple active regions inside one of our pixels. And we wouldn't be able to, what Ryan said, resolve them, which means we can't distinguish them from one another necessarily, because anything inside that pixel is all just counted as one thing. We're adding
one
up all the
bucket.
flux. Yes, one bucket that we're capturing all the photons in, so we can't distinguish features inside that. But the cool thing about observing during the eclipse is it does allow us to distinguish some features and structure, because we can see how the flux in that pixel changes as the moon's limit passes through that beam.
We got our first eclipse.
Oh, go in there. Yes, Dr. Belu is going to share with us.
Hello, hi. Hi.
So
We were just tracking a point on the limb, and we were just seeing the eclipse curve. Just the dropping as down here. Yeah, we are really seeing it on real data.
So we're
This is a
basically,
simulation.
you guys just produced this plot that we're showing here as a cartoon.
We are seeing on the right part.
Oh, Ryan's gonna share it. So he's gonna share the screen.
Oh, perfect.
Bailey, you wanna show?
See some data in real time. Yeah, Belu, sit down and
Yeah,
tell us
sit
what
down.
we're seeing.
No, I think I had better stay there because I made a typo there, and that's why we had a little problem. So as what you are seeing is a drop in the signal because the moon is blocking the light. So we have a straight edge, moving across. So from the slope, we can get how much signal has been blocked within, say, 1 or 2 seconds. So that gives us the highest angular resolution. So basically, you know.
Yeah.
So
How much of an improvement in angular resolution does it give us?
normally this channel, but it's channel 10. This has a, you know, normally you get about a 4 arc minute beam. That is a 4 arc minute is a 40 arc second. So, but with this moon's edge going across, we should be able to get a 1 arc second.
Wow.
So that at one direction only, because the other direction we are still stuck with the, you know, beam is circular.
Right.
So we still have 240 arc second on one side. So it's like what we call a fan beam, or, you know, a long beam, very narrow on one direction and broad on the other.
So our direction of really good angular resolution is the
Right,
direction
that's
perpendicular to the sun, to the moon's limb.
From along the moon's limb, it is a long, but perpendicular to the moon's limb, it is very narrow.
Uh-huh. Right. So what we're seeing in this plot here, this plot in the bottom right, that red line is representative of the flux that we're getting from the telescope.
Yeah, how the
function of
flux is decreasing as the moon is slowly blocking the light from the sun.
Uh-huh.
Yeah. So when the moon moves 1 arc second, the light within that 1 arc second width on the sun is decreasing. That's what we are measuring.
Uh-huh.
It's good. Okay. So I'm excited. Now we are almost
It's almost
got
down
out
to
of
zero.
the beam, so it will going to 0.
Mhm.
So then we will go to the next region and then we will do the same drama again.
Uh-huh. Okay, drama's a good word.
So,
Right.
yeah, and the players are the sun and the moon.
That's right, yeah.
They are good.
We
they
are the
good
audience.
players for the drama.
We are the audience.
Yes.
Okay. Thank you, guys.
Thank you, Belu.
Sorry.
So yeah, as that eclipse curve, that flux curve goes down to 0, that just means that the moon is completely blocking the sun from the view of our telescope, which, as Belu said, means it's time for us to move to a different active region.
Okay. We are also taking little breaks to use our Eclipse glasses to go outside and look at the sun. So that's a really fun thing. Maybe Marinda, you want to go try that and have
Yes.
Erica give you a little break?
Yes, that would be
Okay.
great.
So, and then maybe when you come back, what I'd like to talk about is why it's important to look at the eclipse from multiple wavelengths and from optical, you know, why do we use radio? So maybe we can talk about that, but I want you to have an opportunity to see what we're talking about. So, yeah,
I'll be back.
all right. And Erica and I will continue to monitor the chat and the questions. Looks like some of you are still hanging with us who have been here since the beginning. And a few of you have joined us more recently. So please make sure to let us know where you're joining from, any questions that you have, any experience that you've had with the GAVRT project. And I don't know that we, please put those in the questions. GAVRT, what does it mean to operate the antenna? That is the perfect question because Erica is one of our operators, and I think that she could take that question for us.
So we have mission control here at the Lewis Center at the in Apple Valley. We have mission control where we are able to remotely operate the discs out. I'm not centered. I'm trying to get into the camera here.
Closer to me.
Get closer. So we have the ability to remotely operate the dishes from here in Apple Valley. We can dial in whichever project we're working on. I know Lisa mentioned that we have 4 different projects or missions that we're working on right now. We can dial into whichever dish it is that we need to use for that specific mission, and then we actually just remotely operate it from here. It was like GoToMeeting and Zoom before it was really cool. You know, we've been doing this now for a long time. So fortunately,
1997.
being
when it was
able-
a fax machine,
Yes.
and we used to ship a computer.
yes, and being able to move 1 million pounds of metal remotely comes in pretty handy, let me tell you. Yeah.
So, yeah, so your students would see, or your participants, doesn't have to be students, would see this screen.
The screen just like this,
Yeah.
yeah.
And you would have either Nancy or Erica there to guide you through. The participants will record some of the data as you go through the session, and they'll talk about the context of that data, what it means, what we're looking at.
So as a teacher in the classroom, if you're participating, we will send you all of the sheets you need beforehand. That way, when your students are participating, they are ready to go with everything right there in front of them. They'll dial in, we explain and teach them about all of these windows and what they do, and get everybody dialed in, and kind of a little mini training, if you will. And then when the time comes, the students actually get to move the dish to the source. And
So how do they do that? Do they use their computer, or how do they do that?
they do it straight from their computer. We give them access and they're able to control it. They go in and pick our source and they click track. And then we have a little video where they can watch that dish moving across and coming into focus on the point. It's always so exciting when you see the kids get excited that they've moved that dish. It's palpable to see it. It's one of my favorite things, I think, doing the sessions is when they all start getting excited.
I did
Look,
that.
it's moving, I did that. So it's really, really fun to work with the kids and be able to have a hands-on from, miles and miles away. We work with schools all over the world. So it doesn't even need to be here in California. We work with Arkansas, we work with Germany and Chile. So definitely equal opportunity for everyone across the globe to be able to take part in the science that we can do here through the GAVRT.
So the way to connect to a session is very low. It's very easy to access. So really all you need is one classroom computer, but generally nowadays, especially in a school setting and in the States anyway, students are one-to-one, but you really would just select, or the teacher would select one student to go ahead and move the antenna.
Be the operator.
Be the operator in the space. And then all the other students, generally you would project that, and all of the other students watch. They're all taking down data and participating in the session. They all have an opportunity to ask Erica or Nancy questions. And they don't have to be, I'm sure they're not always directly related to the session. Sometimes it's like, what is it like to work for NASA? And different cool questions like that.
And what we have done is we take turns with the operator. So the different students in the class at different times have a chance to actually be the operator and do the movements.
So, yeah.
I was just going to mention too that the SETI program is really great for those one-to-one classrooms where every student can be analyzing a frame, so you have the engagement of your whole entire class or group or jamboree or homeschool group or whatever it may be. But every student can connect to analyze our search for extraterrestrial intelligence frames, and they can each see if they find life out there.
So, Ryan, what does SETI stand for?
I stand for the search for extraterrestrial intelligence.
It does.
Which is very hot right now.
It is. And I think undergoing a nomenclature change to technosignatures.
Technosignatures. As opposed to biosignatures.
Right. Yeah. So Dr. Levin was fantastic and got a grant and was able to bring the SETI program to GAVRT, and had just really terrific engagement.
Yeah, so I think a little bit later we'll talk about the 4 different campaigns that we have with GAVRT, but SETI is one of them. And like Ryan said, it's really great because you don't even have to be live on a session. You can look at all of the data that other groups have, or other participants have collected, and then you can see if there was anything that there was a candidate, right? Something that looks like potential technosignature.
We have files and files that have not even been processed yet, so we can definitely use the help from our citizen science community on those. In fact, I was looking at a few of them yesterday. So it is very easy, and once you get the hang of it, it's really fun because you look for those pinpoints, and what we're looking for is they call it a candidate. So you're looking for a candidate signal. And then if we can repeat that candidate signal in the exact same place and time on a separate scan that was taken on a different date, you have something. There's something that's repeating.
Our scientists are going to want to look at that.
So that's when we start waving flags and saying, hey, look at this. What is this?
So, I mean, by participating, you definitely have a potential to really
make a discovery or to really find something significant. And Solar Patrol is one way, the work that we're doing today and that we plan to do as we collect this data and analyze it. And then SETI is definitely another way.
Sure.
While we're mentioning them, I might as well mention the other two. So we also have Black Hole Patrol. So of course, looking at black holes or observing black holes is very exciting. And then our longest standing GAVRT campaign is connected to the Juno mission. So that is our Jupiter Quest.
Jupiter Quest.
Yeah, and so at different times of the year, that's a really fun one to do. So let's see, we have a couple who have joined us. Chris, I want to welcome you from Aurora, Illinois. Chris has just completed the GAVRT training with Nancy, and we are excited to have your students engage as well. Chris, I'm wondering what grades you're teaching and maybe what subjects out there in Illinois. And then Eileen is joining us from Texas, so she's pretty lucky. You're retired now. Oh, so anyway, Eileen, here's another little secret about the GAVRT project. We are, some of our best colleagues are those who are retired because they are able to dedicate some more time to GAVRT than they did before. But you used it in your classroom for 20 years, from 2001 to 2021. That is awesome. So you have done several of our projects. So the Quasar project, so that is now Black Hole Patrol, Uranus, Jupiter Quest, and it taught them how to work as a team. So that is really great. I think that's one of our biggest things. And science team doesn't, the collaboration of a science team is very different.
It's very fulfilling.
Yeah, it's different than being a teacher. I will say that. Yeah. So the first time that I was invited, I'll share this little story. Something that I've learned as a GAVRT educator. So one of our papers, it was the peer review process, and I was invited to join the conversation, and our scientists were really going at it. So like in a way that was just really debating about how the data was presented, the analysis, just every aspect of the conclusions and the results that were put in, proposed in the paper. And as a lifetime educator, I realized that as teachers, we are very sensitive. So if somebody were to challenge our work in that way, I think that we would have had a lot of hurt feelings. And so I think that we tiptoe around things a lot. And rather than directly like just challenging our thinking and our results, like we're not really good at that as educators. A lot of times we get oversensitive, and maybe that's an overgeneralization, but in my 27 years in education, that has been something I've observed, or even myself have been sensitive. And so I think that I learned more from being part of that process than maybe anything else. And I've really taken that forward in my career. Like, it's good. I want my conclusions to be challenged. I want my process to be challenged, because that isn't rude. That's professional. That's a scientific method.
Yeah.
And I really started to understand what peer review meant and why it's so important and so powerful, so that when we're publishing things, we know that they're carefully vetted. So anyway, that's something that your students would have an opportunity to do. Eileen, we're really excited that you are joining us. And Eileen taught at Norman North High School in the Norman public school system there in Texas.
Nice.
All right. Clouds are clearing now, so Eileen's going to be in and out. She's going to take pictures. We'd love to see them if you could post anything. They're on the 4-minute, 50-second line of totality there in Leakey. So Eileen has that really cool opportunity both to view the eclipse in totality, and then also to join us as we're collecting this radio astronomy data.
Yeah.
So
that is really
yeah, that's really cool. So I think that's one thing that I've really learned too, like all the different perspectives, and then joining all the data that are collected in these variety of ways really tells a much more detailed story than if we were to only view it with our eyes or only view it in the radio.
So I know out here in California where we are, we have about 80% coverage. So we won't get to see the full annularity, but it's still an amazing partial eclipse. Yeah. 80% is a good one.
We're still running out there with our
We are.
classes.
Our classes,
Chris, that's exciting. So Chris teaches outdoor education courses to undergrad students, and then he helps lead STEM summer sessions for high school students. That's really neat. Here at the Lewis Center, we don't do much work in post-secondary, but we do have our campus here in Apple Valley, in addition to having a mission control, which is really cool. We also have 150 acres, and 100 of those acres are in wildlands, and there's actually a river that runs through our property that is unique in the high desert, because it's the Mojave River, and most of the times it runs underground in most other places. But right here on our campus, there's a granite shelf, so there's always water there, and so it provides really great outdoor opportunities for our students. So we have other environmental programs and other outdoor programs that we love to do. So Chris, I'd love to hear about some of the cool stuff that you're doing. One thing that's really also great is that just learning from each other is important. Okay, so Eileen, now I'm going to be really interested in your updates. Okay, so they're using the Solar Snap Eclipse app. Say that 3 times fast. Solar Snap Eclipse app to take pictures with our cell phones, and it was obtained from ASP. Very cool.
Nice.
Yeah, so the Solar Snap Eclipse app. So if you guys want to download that, or if you are able to obtain that from ASP, that would be a really cool thing.
I'll have to go check that out.
Yeah. And Eileen is still working with Astro students in Oklahoma, and she runs workshops for teachers and students. Yeah, and she wants to give a shout out to Nancy. Nancy's over there doing operator work. She says, hi, Eileen. All right.
I'm at 0-0 right now.
Okay, the team is over there.
They're so serious over
They're
there.
very serious. Okay,
Ooh.
so trying to peek up on a hot spot, says Nancy.
All
All right, Chris. Yeah, Chris, we're really excited to have you here. We'd love to collaborate in all aspects of STEM education. We're really passionate about that, and we feel like GAVRT is one way to teach kids about the scientific process and some of the examples that I shared recently, but also it's a way to bridge our network, right? So we would love to link you to other citizen science projects or other NASA education tools and resources. We love to work together with other projects and even things that are outside of that, anything that's related to STEM education. So
For sure.
one of the greatest things is that it joins us from all over the world, scientists and educators and informal educators, and then we're able to share all the neat tools, whether that's the app that Eileen just shared or really cool programs that we're doing in our areas, and it really does make us a stronger ecosystem and network. Okay, Sandy, what is the team in the background working on? Are they moving the antenna?
They are focusing in on a hot spot right now, waiting for the
Oh wait,
wind
Nancy's
to
gonna
cross
come over.
Oh, here comes Nancy.
Here comes Nancy. She's gonna tell us. I'm gonna switch out.
It'll be real quick, then I'll go back.
Okay. So what we did was we moved the antenna to the sun, and now that the eclipse is starting to come over, we are trying to pinpoint the active regions. So as we are pointing at the active region and the moon starts to come across, we can see the power levels drop. And then we'll do that for a little while until it's almost done, all the way covered. Then we move on over to the next active region. So it's in order to get better resolution of that active region while the moon is crossing over. I think, Maureen, you probably talked about that a little bit, huh?
Yeah, we showed the
Yeah.
map of the moon's limb passing in front of the aperture telescope.
Yeah.
Region and stuff.
Yeah. Okay, great. That's about it. So it's just, as everything's moving, we're trying to just tweak up on where that active region is.
Dial it in.
Dial it in, and then get their measurements, and then wait until we can move on to the next one.
All right. Thank you, Nancy. It is fun watching the team over there, and everybody's into the systems, and we can see everything that they're seeing on our
Yeah.
screen right here.
That looks really cool.
So this is what they're looking at. As you can see on the raster scan, that big blue box The red and the orange right now, those are the hot spots that are being read. But as the scan progresses, as we find warmer hot spots, those will actually tone down and the hotter hot spots will come up in red. So you'll see this map change as the scan is progressing.
So we have some who are just joining us. Again, we would love to see where you're joining from and any experience that you have with GAVRT. And then also we just want to be really interactive. You're going to see our team members jump in and out from this view. And then, and we are just, so if one of us can't answer the question, we're going to tag in somebody, one of our other teammates. And so looking at the Eclipse right now, we're zeroing in on a hot spot and you see the raster scan building there. And also we're available to talk about other things as we're kind of waiting for the scan to happen.
For sure.
So I'm adjusting a little.
There you go.
All right. So we're adjusting a little. All right.
That's what happens when we get excited and start jumping around in our chairs, stuff shifts.
Azimuth and elevation. Who wants to take that one too?
Azimuth and elevation, Maren, do you want to take that?
Sure, yeah.
Want to tap back in? Do you want to? You can stay. I can. I'll tap up. Although this would be a good test for me to see if I can. But when there's an expert in the room, I will try to defer.
He's like, run magnetic field, go. Yeah, so what we're looking at here is the control panel again. So as Lisa and Erica were saying, the raster map's appearing over here on the right. And then over on the left, we can see where the telescope's pointing. So it's giving us azimuth and elevation coordinates. So elevation, you can think of as sort of, yeah, exactly like this. So 0 degrees elevation would be at the horizon. 90 degrees elevation would be pointed directly up, or what we call zenith. And then everything in between from 0 to 90 is your range of elevation values. And then you can think of azimuth as like the other direction if you're in spherical coordinates. Yeah, like scanning around like this. So that can range from 0 to 360, or usually we do plus or minus 180 degrees.
Now the dish does have mechanical hard limits, so we can only spin azimuth a certain way, and then we actually go back the other way and patch it on the other side.
Oh.
Because we don't want to stretch the cords too far. So we always need to make sure we're keeping our mechanical limits in mind and going the right way with our dishes. So.
Yeah, I guess in that case you're worried about cable wrapping, or like the physical antennas moving and all the stuff that's plugged into all the stuff in the antennas wrapping too. So you don't want to
same with the up and down. We don't want to measure anything on elevation that's too close to the horizon because we don't want that dish to hit the ground.
Oh,
so we have to keep a certain elevation is where we want to start observing and never really go below that. We got to be mindful of that. They can reset it, but it's taking somebody to get out there at border when get out there and mechanically fix it, and then we're back in business. But if we don't push the limits, it's okay. We don't want to do that.
Yes, don't want to break anything. What is the lowest elevation that we can observe at?
I believe it's 10 to 17.
Limits at 7, and then there's a hardware free limit at 5, and then there's a final at like 4.5.
So software limits at 7. We'll go with that. Then there's a 4 and a 5 for the hardware, but we don't want to push it too much more past 7 on the elevation.
Yeah. So it's nice that they give multiple limits.
Yeah.
You have to breach 3 limits before you break anything.
Then yes, for sure. I don't want to be the one to make that call.
So yeah, we can see the map building slowly here. I see a really nice hot spot on the northwest-ish limb, part of the limb here, or part of the sun, rather.
So can we bring up Helio Viewer?
Yeah. So I actually have Helio Viewer open up on this guy. We'll take over screen share somehow. Bear with me for a moment while I figure out how to control the webinar here.
Yeah, one thing I was gonna say is there's all different kinds of limits in both azimuth and elevation. So no.
Be on camera.
Joy. Yeah, the software includes limits. And then heaven forbid those software limits failed or anything, or when you're in open loop where you are manually controlling the antenna by inputting a voltage into the motors, which is how it's done. Closed loop, there's a servo loop that is constantly taking feedback from the encoders and tells you what you're doing. So when you're in open loop though, some of those protections are not in play. And so at 7 degrees is where the software limit says don't go any lower. 5 is a pre-limit. There's a hardware switch that you can clear remotely. And then the final limit is around 4.5, and that's a final limit. Somebody has to go out there and manually move the antenna from where it's at. It's essentially stuck until somebody goes, takes a look at everything, make sure that there's no safety issues for the antenna, and then they back it out. So limits are a good thing. It protects us from ourselves.
Very good.
Thanks, Ryan.
No problem.
All right.
You said you could continue to tell people.
I mean, we're using.
Maybe.
Yeah, we're on channel 10.
So what we are looking for right now is the helio viewer, which is a visual representation of the sun. That is from the Soho, right? Helio viewer, is
That's a
that a
good
Soho?
question. I actually don't know the answer to that. We can look this
Their
up on the
Soho
fly.
Observatory, I do believe. We'll confirm that, but they have ways of viewing the sun from up close and personal. Right now, Soho is actually around the sun. So Soho, of course, is not going to see the shadow of our moon going across it, but it does register all of the hot spots and the sunspots that are currently happening. It also sees the flares, it sees the CMEs. So when we were referring to where are we going to look on the sun for this project today, for this experiment, we did refer to Soho, to the helio viewer as well, just to make sure, hey, look at this one, let's look at this. Can we pull that up on our radio antenna and see it? And that's one of the ways we kind of process of elimination, went through and picked where we were going to stare at today.
Yeah, it's one of the reasons why it's really useful to have a multi-wavelength view on the sun.
Absolutely.
Because we get a lot of information at different frequencies, at optical frequencies, that can inform us where to point our radio dish to collect data on specific active regions. So
Yeah.
multi-wavelength observing is really powerful in all of astronomy, and for our case right now, it's really helpful for
It is.
solar physics.
Because, you know, we can't just run out there and look with our solar viewers and say, hey, that looks like a good spot. For us, it's probably not a good thing to do.
Lisa, do you know how to switch the screen share?
Yes.
We
I want to put up helio viewer.
Yeah, if you could shift it back to me, maybe, Ryan.
There we go.
Oh, I was like, I could go. Okay.
Okay.
All right,
And then
here we
also
go.
there, before you, or at some point, I don't know when would be, how long does it take the antenna to move? I think it depends.
Uh-huh. Yeah, that's a good question.
Another
Question before we show helio viewer.
Yeah.
So DSS 28 is very unique in that it can go really fast. So the maximum speed at which it can move is 3 degrees per second. We keep it limited to 1 degree per second when slewing. So slewing is when you're trying to go find a source or a target. And so that we throttle it back to 1 degree a second. When you're tracking though, there's something called sidereal rates, which I'm going to have to defer to Marion on. I know we're all trying to play tag here, but it's usually about 7 millidegrees per second based on the rotation of the Earth. Does that sound right?
Sure, that sounds right.
Yeah, that's it. I think that's about what it is. So assume you're looking at a spot in the sky that is not moving. The thing that is moving is the Earth, and so we have to move the telescope to offset the rotation of the Earth. So the answer is just like Dr. Lamb said, it varies. So We can go 3 degrees if everything was wide open. But in order to protect all the gears, the motors, everything, we slew at 1 degree per second.
Nice.
Yeah.
Cool.
Yeah, I guess we were talking about that earlier too, like the antenna has a lot of moving parts and you definitely want to protect it.
A lot of moving parts.
And also because it's for educational use, of course, it's not the same priority as if we were tracking for NASA spacecraft or something like that. So we have to take really good care of the resource that we were given, the tool we were given.
Yes, yeah. So yeah, this is a view of HelioViewer, which Erica was just talking about, where we're getting a really nice view of the sun from a space telescope, which we think is SOHO, but I'm not 100% sure about that. I'll look this up. And it's showing us basically the surface of the sun, and we're seeing bright spots, which are those active regions that we were referring to before, which are bright spots in the corona of the sun. And actually, I'm going to zoom into this source, which we were talking about earlier in the broadcast. This was our first target in our GAVRT observations this morning. So we were pointed here while the moon's limb passed between the Earth and the sun. And there's some really cool structure that I want to point out here. So what you're seeing are some what look like little loops coming off the surface of the sun. And those are loops. It's really hot plasma that's heated up to millions of degrees Kelvin. And the reason that they're forming that looping structure is because the plasma is basically tied up to the magnetic field of the sun. So what we're looking at here is actually the structure of the magnetic field of the sun in the corona.
HelioViewer is a really neat tool.
It is, yeah.
Yeah.
It's so cool. There's so much information in here that you can access. I like this. It shows you what the Earth is for scale. So
Just in that one active region, we are a tiny little, it is so much bigger than our whole planet.
yep, we'd fit right into one of those loops. No problem. So yeah, this is a really cool tool. And I'm seeing that it's showing at least, maybe these are SDO images. So that's the Solar Dynamics Observatory. It looks like we're actually looking at the sun at UV wavelength. So this 304 here, if you all can see my cursor, that's the wavelength that we're observing at in angstroms. So this is actually probably a UV ultraviolet view of the sun. And I think this is nearly live. Looks like this is coming from 1505 UTC. So just about 40 minutes ago.
So
Peaked up on 462 right now.
peaked up on 462.
All right, let's zoom out. And if I'm right, I believe this is what Ryan just referred to as 462 or active region, some leading digits ending in 462.
Yeah, AR 13462.
AR 13462. Thank you. So super cool. I'm going to go back in time just to get the tags working on this image. So yes, that was right. So this is the active region we're currently observing. National Oceanic and Atmospheric Administration, I think I got that acronym right, NOAA, has designated this to be active region number 13462. So that's how we refer to these by name. So we started over here. We're now targeting here as the moon's limb is passing in front of this particular active region. And then after that, once this region is fully obscured, we're going to jump over to AR 13465 over here. Super cool.
Very cool. All right. Tell me, Ryan, when you guys want to switch
Okay.
the view. There's a few of you I don't think we've heard from in the chat. Love to see where you're joining in from. You have like Frederick and Greg and
Oh, I see my dad's name.
James. Hi, Dad. Aw, Mom and Dad are here. Yay!
James.
James, yeah, okay. I saw that earlier. I was gonna ask if you had a brother.
That's my dad. My parents are probably in different rooms of the house just watching me on there.
Yeah.
Aw, man.
Mr. Nakatani is on the web. Our two board members, Yolanda and Marisol, are hanging in.
Maya, love to hear from you. So go ahead and put in questions, just where you're joining from, what questions you have, any experience you've had with GAVRT. We'd love to keep this as interactive as possible as we go through and as the data is coming in. So anybody who's just joining, of course, this is a fluid audience coming in and out over this window of time of the eclipse. So a question for anybody who's just joining, maybe we should go back to what is an active region? So here in Helio Viewer, we're looking at active region. What does that mean?
Yeah, that's an awesome question. So an active region is basically a hot spot in the atmosphere of the sun, or the corona, as we've been talking about. The corona is this tenuous plasma that surrounds the sun, and it's much hotter than the surface of the sun, actually. So the surface of the sun is about 6,000 degrees Kelvin. The corona is millions of degrees Kelvin, so much hotter. And the active regions are portions in that corona where we have a lot of magnetic energy, a lot of magnetic flux, and it presents in these ultraviolet images of the sun that we're looking at now as a really bright spot. And these active regions are found above sunspots that we see on the surface of the sun in the photosphere. So these active regions are what we're targeting with our GAVRT antenna right now. And what we're interested in seeing with our GAVRT radio observations, so not at ultraviolet like we're looking at here, but at gigahertz frequencies that we're observing with GAVRT, we're looking at something called gyrosynchrotron emission. And that's basically what you get when you have an electron in the corona, in the atmosphere of the sun, gyrating around a magnetic field line. And so we were just looking at some of those magnetic field lines over on the west limb of the sun. This is a nice example of some magnetic field lines. So you're actually seeing here, if you follow my cursor, those loops are representative of plasma that's emitting at, in this case, ultraviolet wavelengths in that loop because it's following the magnetic field. So this loop represents the structure of the magnetic field in this part of the sun's corona. So that gives you an idea of if you picture a bunch of electrons and you gyrate them around those loops, you get something called gyrosynchrotron emission. And that's very bright at gigahertz frequencies, which is where we're observing with GAVRT. And it turns out that the frequency that you observe, that gyrosynchrotron emission, tells you information about how strong the magnetic field is. So at particular magnetic field strengths, you expect particular frequencies that you observe at. And so by observing these active regions at particular discrete frequencies, we're seeing different magnetic field strengths. And typically magnetic field strength gets weaker as you move further out from the sun. So you're actually getting structural information about the corona in terms of height by measuring this radio emission. So stronger magnetic fields means you're probing deeper into the corona. So we can get a lot of information about the vertical structure of those active regions, as well as just the structure in the perpendicular dimension as well.
I guess I have a question too, like why does it matter? Why do we want to know what's happening in these active regions? Like how does it impact us here on Earth?
Yeah, that's a really awesome question, Lisa. And that gets to why a lot of astronomers are interested, a lot of solar physicists are interested in observing during an eclipse. So we were talking about that corona being millions of degrees Kelvin,
right?
So much hotter than even the surface of the sun. And that's a huge mystery still in physics. We don't really understand why or how the sun is able to heat its corona to such a high temperature. Usually, if you think about maybe you have like a fireplace or a bonfire, usually it's hotter when you get closer to the center of the source of heat, and it gets colder as you get further away.
And it's
this is the opposite. Yeah. Suddenly you're getting further away, but it gets really, really hot,
way hotter.
So what we want to do is we want to study features in the corona, like what we're doing with GAVRT today. And that can help us learn about how the sun is heating its atmosphere to such a high temperature. We think the answer has to do with magnetic fields. And this is a joke in astronomy where like if there's ever a question that hasn't been answered yet, the answer is probably magnetic fields. Magnetic fields is the answer to all mysteries. And we don't really understand magnetic fields, so that's probably the answer. In this case, we really do think that it's the magnetic field of the sun that's providing the heating mechanism to the corona. So we talked a little bit earlier about things called flares and coronal mass ejections. So those are bursts of energy in the case of flares, or huge release of plasma in the case of coronal mass ejections. And that's caused by magnetic fields basically going from really high energy, twisted, complicated configurations, snapping back down into a much simpler configuration. And because we need to conserve energy, if it snaps back down to a simpler configuration, all of the energy from that more complicated configuration has to go somewhere. And we think it goes into heating the corona.
Okay. And does that have any impact here on Earth?
It does, yes. So NASA is very interested in being able to monitor and predict for those kinds of things we were just talking about, flares and coronal mass ejections, because they can have a huge impact on Earth.
Yeah.
So coronal mass ejections can be very damaging to satellites in space. They can be damaging to astronauts that are in space.
Yes.
And if they're large enough, powerful enough, and happen to have the right magnetic field configuration within the CMEs or coronal mass ejections themselves, they can actually do an intense amount of damage to structure on Earth, particularly things like power lines. There was a really strong CME that happened, solar storm that happened, I want to say 20 or so years ago, I can't quite remember, but it basically caused a blackout in Canada and a significant fraction of the Northeast. So NASA is really invested in being able to predict
space weather.
Yes, exactly. Predict this phenomenon that we call space weather, kind of like weather on Earth, but stuff that comes from the sun that can impact us.
Yeah, I think, and that's one thing that I know students are very interested too. Even if you would say, oh, it could impact your cell phone. Yes. Or something like that, then all of a sudden it becomes real. So I think that's one of the reasons why we were really excited as we've worked with everybody to develop Solar Patrol, because it's tangible to all of us, right? All of us can see the sun, all of us are impacted by the sun. Space weather has real, could have real impact on our day-to-day lives. And so I think that it's something that's a little bit easier to connect with maybe than a black hole or something like that, which seems more abstract.
Yeah.
Okay, so, all right, we got an update from Eileen. The Solar Snap app is working well. She's getting, you can see I don't have my reading glasses on, that's why I'm squinting. Getting great pictures without even using the tripods. No cell signal in the area, or she would send them to us. Teaching families around us, and they are in Texas Hill Country. So this is so fun. Eileen, I feel like you're a correspondent from Texas. And Steve, Dr. Levin, is probably on a plane, and so he isn't able to be that correspondent. So I'm so glad you joined us. And then for any students watching, let us know if you're one of our GAVRT students. Would love to hear from you. What types of classes should students take in order to pursue a career in this field? So as you went into radio astronomy, what are some classes you took?
Yeah, so when I went to college, I took a lot of physics classes and also a lot of astronomy classes. When I first went to the University of California, Berkeley for my undergraduate degree, and I got a major in physics and astrophysics.
Okay.
But when I started, I had no idea what I wanted to do. I was taking I took intro to business. I was just lost. But yeah. I knew that I liked physics because I took physics classes in high school. So I thought I'd try that out.
Yeah.
It also turns out that the University of California, Berkeley has a really great astronomy program. So I also took an intro to astronomy class. And I was like, this sounds fun.
Yeah.
Astronomy is like a really cool, exciting application.
I think that's where Steve went as well, right?
Did he go to Cal?
I think he did.
I need to talk to him about this.
Yes, I think so. So
yeah.
First tip, go to Cal.
Yeah.
Accepted to Cal.
Yes, yeah. No, there's a lot of great astronomy programs in the US and throughout the world.
Yeah.
India has a lot of really great astronomy programs. India has a lot of really great radio astronomy programs.
I think India, we have so many great participants from India, and that's probably why. Yeah. Also Chile does as well.
Yes, yeah.
And we have a lot of folks who join us from Chile. And so, but yeah, here in the States, a lot of opportunities. And I think even just talking earlier with Chris and some of the opportunities that he's providing in his undergrad to students, I think there are many, many, many directions. But one thing I liked what you said, and I think that it's really important for our students, is that, you didn't know what you wanted to do. You tried out a lot of things. I think that we have a tendency to always ask kids like, oh, what are you going to major in? What do you want to do after high school? And a really appropriate answer is, I don't know.
Yes.
and we hope that GAVRT gives you a glimpse into a whole bunch of different careers that maybe you had never considered before. So whether it's like being an operator or a scientist or an engineer or an outreach expert, or a teacher. I think that each one of us on the GAVRT team has a totally different niche. And so like I get to learn the science all the time, and then hopefully I'm able to share some education that, you know, perspective, and I love that. So that's one of the things I love most about our team.
Yeah, totally different roles, but equally important, like equally important jobs to make the whole thing come together.
Yeah. And I also do have to say to Marin's mom and dad, you guys have to be so proud, because she's an absolute rock star, and I'm really glad she chose radio astronomy, and I'm also really glad that she got connected with the GAVRT project, because I feel like we're just really, really, really blessed to have you on the
Oh,
team.
that's sweet, Lisa. I'm so happy to be here.
100% true. I wish she could hear us talk about her when she's not in the room, because we are always just raving about how amazing she is. So if I were your mom or dad, I would be so super proud of you. That's cool. That's right.
That is
Erica
cool.
just got a good picture. Did you use that Solar Snap?
I did.
Oh,
Now I can
nice.
say it. Eileen, it's rolling off the tongue now.
Solar Snap app.
The Solar Snap app is working well for us here in California as well. And Eileen loves physics.
Oh,
So
awesome.
another physics geek with you.
Yeah.
Enthusiast.
There you go.
All right.
Quick
Yep.
update from the trenches. We're on the 3rd active region now, so this is 6,
Oh.
5.
We're gonna move over.
Yeah.
We're gonna move over.
6, 5, I'm sorry.
So I think that means we're on this one right here, and let me jump back a day so I can get the tags on there. Yeah, 13465 is this one right here.
Mhm. So this is an incredibly strong active region on the sun right now. Far and away stronger than the other ones that
Okay.
we've observed thus far today.
Nice. So Ryan's, if you couldn't hear him, was just saying that this is the brightest active region that's currently on the sun, brightest by far than any of the ones we've observed yet. So very exciting.
Yes. Let us know if you guys want to switch over to the view.
Okay.
And then really cool. That was a really good question about students. Sarthak is also planning to go into the same field. And so he is looking at, during his bachelor's, majoring in physics with a minor in astronomy or a minor in computer science, as computer science, as the computer science is required in this field too. Absolutely.
Yes. Oh yeah, absolutely.
Yeah.
Yeah, that's a great point.
Mhm.
Computer science, being able to, so much of astronomy nowadays is actually doing computer science. You're coding, you're writing the software that will get used to take your observations, to produce your observations, and then do science with your observations.
Yeah.
So yeah, that's an excellent point.
So also, if you want to work on a project, maybe a deeper dive project for one of your classes or something, we would love to, Nancy and Erica would love to work with you on that. And we actually have a lot of opportunities for creating some things in coding, and we're working on some new data visualization tools and data access. And so if that's something that you're interested in, let us know. And we are looking for more opportunities to work with our participants to actually develop those tools.
Yes, yeah, we need the tools to process the data that we're collecting today. Solar Patrol in general has a larger campaign to observe the sun regularly, create those raster scan maps that we were describing before. And we need the code basically to do all of that, to facilitate participation by citizen scientists out there looking at actual solar data from the GAVRT telescope, connecting it to multi-wavelength data sets like what we're looking at here with HelioViewer. So yeah, contact us if you want to.
Let us know if you want a project. And also, hopefully that's a win-win, right? You get to contribute to the project, and then also hopefully it's really great real world experience for you as well. So, and then work with really cool people like Marin and Belu and Steve and Joe and our other scientists, and then also, of course, directly with our operators, Nancy and Erica.
Yeah.
So, okay, Eileen. You can definitely take more astrophysics for knowing how to code, computer science, electrical engineering, mechanical engineering. And yes, amen. We need science teachers more everywhere. Gosh, yes. In my role here at the Lewis Center, I am the superintendent. I'm called the President CEO because we have charter schools as well as projects like GAVRT. But one of the hardest things, whether you know, in any capacity, any hat that I've worn throughout the educational system, is really finding amazing science teachers who are willing to introduce things like this, where, you know, the teacher themselves don't have all the answers. I think that's something that's really hard for us. To be vulnerable and just like totally go out on a limb to something that we're still learning and trying to understand and then bringing it. But just quality science teachers they are our hardest to fill positions at both of our schools, you know, secondary science for sure. So yes, so if you have a passion, also consider teaching. Erica's actually getting ready to transition from a GAVRT operator into the classroom. So we're really excited for her because we know that she is going to be great and she's going to continue those GAVRT lessons. And it's really a great thing to do. And then Sarthik is ready to work with us. So we'll stay in touch.
Yes.
We'll stay in touch. We have lots of hands-on experiences. So we're excited to make that connection. See, we do have some new folks joining us as I look at the list. Several. Some are hanging in with us all the way from 7 a.m. But others are just joining us. So if you are just coming in, we'll give another little update of what we're doing right now, but please put into the question box where you're joining from, any questions that you have, because our goal is to just be interactive, and then also any experience that you already have with GAVRT or that you're hoping to have with the GAVRT project and how you might want to bring that into your area. And then we do have a cool correspondent in the field in Texas, in the Path of Totality. So Eileen's giving us updates from there. But if you guys, she also recommended to download the Solar Snap app on your phone if you guys want to take pictures of the eclipse. So we are also doing the same, running back and forth outside and putting our eclipse glasses on and viewing the sun. So how are we doing over there, guys?
We're tuned in on the next active region 465 and watching the power drop.
Nice. Okay. Power dropping is good because that means the moon's limb is starting to obscure our field of view.
Do you want, yeah, let's switch over. We're going to switch over from Helio Viewer to our GAVRT screen. And so for those who are viewing, so we are here kind of running commentary and fielding questions, but we also have our operators and scientist team just on the other side of the camera, and they are running the scans. So this is what they are looking at as a GAVRT telescope is completing the raster. So you want to see.
Yeah, so I can describe
go ahead and
what's being plotted over on the bottom right here. So what you're looking at is basically the flux that the telescope is receiving as a function of time. So the red curve is telling how much flux, and you can read that off on the y-axis, and then on the x-axis is time, and it's in UTC, which is universal time. So to get to local time here in California, we need to subtract 7 hours. So we're at about 9:06 local time here, which is about 16:06 in UTC. And what we're seeing is flux from where the telescope is pointing on the sun at that active region that we were just looking at. But I can't remember the digits for. I know it ends in 5.
465.
465.
Yeah.
So we're looking at flux from that active region. It's decreasing over time because the moon is slowly passing in front of where our telescope is pointing. So the moon's limb is obscuring more and more of the flux from that active region. And so we're seeing the counts on our telescope, represented by that red curve there, dropping slowly to 0. Once it does get to 0, then we know that the moon's limb is fully obscuring that active region, and then it means it's time to go point somewhere else. Point to something else exciting happening on the sun. Either the east limb or back to our original.
Yeah, so we're gonna go back to the east limb. Yes.
Okay.
Yeah. That very first one that we observed. So egress will start to occur, and so then that original active region won't be obscured anymore.
Okay, awesome. Yeah, so what Ryan's describing is we're going to go back to the first target we were pointing at on the limb of the sun, and we're going to catch egress now. So when the moon is passing and we're starting to see stuff reemerge on the sun. So kind of what we were doing at the start, but in reverse.
One exciting thing I did want to, tell everybody about is that we are going to be developing a paper out of this, and we'd love for everyone to join us again on this next session. As we ourselves at the Lewis Center try to understand exactly the science and work towards doing a published paper for everybody to look at.
So I see Mr. Nakatani is online. Mr. Nakatani is one of our new math teachers at Norton Science and Language Academy.
Right.
And I don't believe we've gotten our GAVRT hooks into you yet, sir, but I'm very excited to see you online. And so maybe your math students might want to join a session, and that would be a really great thing to do. So
it'd be a great opportunity. I think there's another opportunity as well coming out of today's solar observations, and in preparation for April. We're already identifying a ton of tests, calibrations that we need to do since our receiver was recently repackaged. So there are some good data sets that we need to gather to better understand how our telescope is now responding and acting. So there's the list of things to do is growing by the second.
yeah, we already have a volunteer for a student project on some computer science projects and coding. So excited about that. Sarthak is ready, standing at the ready, and
man after my own heart. I'm computer science background as well, and so there's definitely a place for us.
yes, definitely. Most things don't work without you.
Especially not in astronomy.
Yes. All right. Other questions or other, what about any student questions or teacher questions, or do we have any scientists online? Love to know a little bit more about you. It's part of the fun of this is just coming together as one group, and we all share a common interest, but our diversity is our strength for sure. How's it looking out there, Erica?
We're out there.
Ooh,
that's a cool picture.
yeah. You're using that Solar Snap app?
Yeah.
Eileen, such a great,
We can zoom it in too.
yeah, such a great suggestion. I don't know if you guys can see this. So Eric, this is what it looks like right now using the Solar Snap app. And this is what we're looking like here in Apple Valley, California. So we'd love to see your guys' images.
I'm gonna go outside soon. And
Yeah, no, I know. Great, go. Yeah, go. We'll switch out.
Tap Erica in.
Yes, we'll tap Erica in so that Maureen can get out there and see it. Yolanda.
It has been very fun running out
Yeah.
and taking a look at it and getting the app to work on the phone. I'm excited to get some photos of it in
Yeah.
addition to the data that we're getting here. So have those timestamps so that we can correlate to the plan on the scan.
Melissa, you are working right now on your undergrad in cybersecurity. I can't tell you how relevant I think that is. Actually, a cool fact about cybersecurity, the Lewis Center, our high school here in Apple Valley, has one of the only 10 inaugural cohort junior ROTC programs to transition from Air Force to Space Force. So we are big on cybersecurity around here and recognize that that is just such an important field. So I think that you will be able to do many things, and we'd love to work with you on any projects as we develop them, and anything you can be doing. You know,
That's my sister-in-law.
That's your sister-in-law? What? Oh, well, Melissa, you got the hookup. So we'll definitely work with you. And we think that that you're going to have your ticket written. I'm wondering, are you going to Cal State San Bernardino? You know, should you go into Cal State? One of the best cybersecurity programs in the entire
I don't remember.
world.
Oh, that's horrible. I don't remember the name of her program right now.
You feel.
I just bad.
Okay, so Eileen just put in the link to order the Eclipse. Okay, so I'm going to put this, Eileen, into the chat. This is the link to order.
Oh, the solar.
Yeah, the solar app.
Nice.
Okay. Southern New Hampshire University.
That's what it was.
SNU, right? I
SNU,
had a friend,
yeah.
well, I just finished my doctorate a year ago, and one of my friends had done her grad school there at SNU. So they have a good reputation. Very cool. We'd love to work with you on a project. You know the right people. Yes. All right. Let's see. Power. Frederick, we haven't heard from you. I'd love to hear where you're joining from, and maybe are you a student or a teacher or a scientist or just a space enthusiast?
You know, being a space enthusiast is pretty much what led me to GAVRT.
Yeah.
Just since I was little, I've always been interested in the eclipses, and I had the added benefit of having George Air Force Base right here when I was growing up. So of course, all of the Air Force and the shuttle launches and everything was so interesting to me. So coming into GAVRT felt kind of like coming home for me. So
Yeah.
it was so exciting when I was able to join the GAVRT project and say, look what I get to do.
Yeah, I feel the same way. Actually, to be honest, I really wasn't a space enthusiast. I was an English teacher.
Yeah.
And then I was fortunate to get a job at the Lewis Center teaching 6th grade. And I was like, what is this GAVRT project? And I had a little background in curriculum and instruction, and I was invited to work on some lessons for GAVRT, and I was hooked ever since.
Yes.
And I still pinch myself that I get to work with such amazing people, and my whole perspective has changed. I think just realizing how humble everybody is, and that they're just
Really, yeah.
like enthusiastic lifelong learners.
Approachable if we have questions,
Yeah.
and always willing to jump in and answer questions or even talk with people.
And we also have, I don't have my glasses on, so I'm so sorry. I know I'm butchering your guys' names because I can't really see. Also joining us from India is Kruthika. I think I'm saying this wrong, but you're working in the field of PLC. So I'm wondering, PLC, that acronym means something different in the States in education. So I'm wondering what PLC means, but I love that you're fascinated in space science, and we want to connect you with GAVRT. So one thing I don't think that we've mentioned to you guys is we are going to have another open session that you will receive a personal invitation to help us analyze the data that's collected.
Yeah, so if you're not on the mailing list already, definitely go to mc@gavrt.org, correct? For the email. Send us your interest so that we can make sure we get you added on to the email list, so that when we do send out our email blasts, you will get the information for our sessions.
Yep, I'll put that email, the GAVRT team at MC, standing for Mission Control, at LCER.org.
Thank you.
For any questions,
Added to the mail list.
Our mailing list, but we do have all of your emails.
Yes.
And so you are going to get a personal invitation. So you are major PLC means programmable logic controller. Ooh, yeah, definitely. Again, a really good fit. Ryan's over there giving a big thumbs up to that. So excited to find ways. Like I said, we're developing some different projects specifically to work with a few participants who want to take on a deeper dive project to make our data more accessible to the public. We really are trying to expand from working almost exclusively in K-12 classrooms to being able to have a more open session, so that people can be unaffiliated and you can just join from all different, like we are today, and really participate and work with the data. And so that's something that's forthcoming, and we're developing as we go. And so we would love to have you help with that.
And DSS 28 definitely has a PLC that interfaces with the antenna drive cabinet. So
Yes.
there is a question in there that mentions CubeSats. Lisa, do you maybe want to share the GLEE
Well, we have somebody from Glee on.
Oh, no way.
Yeah, let me go back. Somebody from Glee is on,
Oh,
so,
that's fantastic.
yeah,
I was thinking LunarSats and CubeSats and.
yeah,
Connect them, because they're local too, Palm Springs, I think I saw.
right. Frederick is joining him. He's a STEM educator and he focuses on aerospace, high-powered rocketry, CubeSats, so right, perfect, halves. And you are working with teams in the Palm Desert, Irvine, and San Diego. So here in Southern California, so from San Diego through the desert. So Palm Desert is different than where the desert that we're in, but not too far away. Yeah, yeah, that's low desert, we're the high desert.
That
So
elevation thing again.
yeah, Frederick, excited to have you joining us and would love to see how GAVRT might fit into some of the STEM work that you're doing. Let me go back to see who was with Glee. That was Manis, but I'm not sure if Manis is still on. Yeah, Manis, you're still here. Did you want, Ryan, can I have them unmute at all? Or Manis, did you want to share?
You can manually unmute them.
Yeah, let me know, Manis, if you'd like to share a little bit about the Glee project, and I can unmute you. So just let me know in the questions, and I would be happy to share the mic with you so that you could talk a little bit about the Glee project.
You look at the number.
I'm looking at the X plot
Yep.
here, and the fact that that line is nice and low shows that the moon is covering the spot that we're focusing on the sun right now. So as you can see it go, the line go down in kilohertz, that means we're receiving less heat from the sun right now. So as the moon is passing over that spot, that's where we're receiving the low numbers, and then as it passes back over right at that edge is where we're going to be seeing it start to spike up again, and that's where we're going to be getting our important readings for the science experiment that they are so excited about over there. Oh, I just heard a wow.
I did too. And then Manis, just by way why we were excited about Glee, we just had an introduction from one of the scientists who we worked with for a long time, Dr. Brian Day, and he just introduced us to Emma Hobson, who is also part of the Glee project, and we are looking towards seeing how we might collaborate with our projects together. So I'd love to hear more from you and to share a little bit more about the Glee project. Okay. All right, so Sandy is asking a question about the screen we're seeing. What do the X and Z boxes in the top left-hand corner refer to? So here, X band and Z. These.
Oh, the little blue and the orange squares, those are the different
13.
satellites. So DSS 13 or DSS 38.
So what was the question? Sorry.
So here, come over here.
Come on over.
So what are these? So X and Z, what are these boxes here?
orange and the
So
blue up
yeah,
top.
these boxes here.
Yeah, so XPlot is a strip chart of the data that's coming into the antenna. So particularly on channel 10 right there, we're looking at X-band data that's coming into the antenna right now. So X and so all the X's are because we're on a Linux-based system, and it's all written in using X11, which is the windowing system. So I'd love to give you a cool answer, but it's because X11 is all of our windows. So X antenna control, X plot, and then Z plot. That one's actually Z plot due to the three-dimensional aspect of it. So we have X, Y, Z planes that we can look at for the data. So you have 3D representation as opposed to a 2D, just a X and a Y.
Okay, that was a good answer. Yeah.
It sounds like they are.
Yeah.
Oh, there's a new raster
coming.
Okay.
Yep. So you'll see that building here. No.
One thing to show, we are at the interlude of our program where we're doing a raster right now. So we just started doing a 13-minute raster.
So this will help us to really see those active regions and make sure that our pointing is good as we go back to the active regions that we started with as egress occurs.
Nice.
No, you don't see the activity. It's behind the moon.
Oh, yeah.
So, no,
We'll get
Yeah.
a picture. No, there is. It's a cool effect.
Yeah, that's the cool effect.
Yes, there is a cool effect.
Cool
The
effect.
I'm hoping you're hearing the conversation that's just happening on the backside of the camera, not the backside of the moon, but the backside of the camera. So we have Ryan and Belu talking about what we're going to see in this
Are there
raster
any
scan.
in the southern region that might
Southern region will show.
It will have, well,
Yeah.
are there any active regions down
Yeah,
there?
down below there.
Yeah, so, well, we'll see that one.
Oh, nice.
We'll see a nice crescent shape in the.
Yeah.
That's the shape of the.
Absolutely, yeah. So we'll get a great image of what the moon looks like in front of the sun.
Nice.
In radio at least.
She said that's the shape of the moon. Sun.
Oh, I said moon. Yeah, crescent shape of the sun. Cloud by the moon.
We're never used to seeing crescent shape of the sun, right?
Yeah.
Mm-hmm. So over the next several minutes, you'll continue to see this raster build.
So I actually just received a text message from someone saying, what do I do if I don't have glasses to look at the eclipse? So as we
Oh,
talked
do you
about a
wanna
little
do
bit
another-
earlier, if you have a piece of paper at home, you can just take a pencil and poke a pencil through it, make a nice little round circle, and then you're going to hold it up so that the sun is going to shine through that circle. The shadow on the ground is what you're going to look at, and it will show you the little crescent shape of the sun. Another thing that I've used in the past is you can use a colander because it has all those nice, beautiful little perfect circles in it. Look at the shadows on the ground and you'll be able to see the crescent. Don't ever look directly at the sun unless you have our fancy solar viewing glasses. You'll know they're good solar viewing glasses because when you look through them, you don't see anything until you're looking at the sun.
That's true. It's very dark. So don't put them on until you're in position.
You want to get outside, know where the sun is, and then put them on.
If you're anything clumsy like I am, get in place and then put them on. All right, starting to build. This is one thing that I love about Solar Patrol is that we have a great visual with raster scan. So a lot of times we will pull this up and then look at Helio Viewer as well, and so we can make some comparisons. All right. Right.
So it looks like it repositioned a little bit. As the scan is running, you'll see that there may be a big bright red spot. And then when the next row of data comes in, we might find a brighter spot. So it will recalibrate everything up top to be able to bring the brighter spots forward. So as you see it changing as that scan is running, that's kind of what's happening.
It's kind of fun with getting reports of what people are seeing with their eyes.
Around the country, around the globe.
All over.
Around the globe, it's
All
amazing.
over. I'd like an update from Eileen. How's it looking in Texas?
Do you want to run outside and take a look?
No, I think others are. Got our team running in and out. All right. Yeah. It's time for Belu to be able to run outside and see. He's been hard at work.
Snack time, that looks like.
Yeah. Still several of you are joining in. Sandy, Melissa. I don't think we've heard from Maya. Maya, we'd love to learn a little bit about you, or Maria. Or Dazana. And Anne and Anna and Aaron, love to hear from you a little bit. If in the question box you just wanted to put where you were joining from, a little bit about yourself. Also, Manis, if you are where you can hear us, we'd love to unmute you and have you share a little bit about the GLEE project. So that would be exciting if you were able to share. The GAVRT project is looking forward to teaming with the GLEE project. So we just had that introduction recently. And are excited you're joining. Yay. All right. So this process is, you know, going to take just a little bit of time,
This is
honestly.
a 13-minute scan. So,
Yeah, so it's not really long compared to some of the other scans that we do.
yeah.
Eric, you want to talk about like during a regular GAVRT session, if they were doing solar patrol, what the class might be doing as the raster is building?
So during solar patrol, as we are running a scan on, well, I haven't actually been through a solar patrol session yet, but so I think that would be more of a Nancy question, actually.
We'll talk about that in a second. Now we're looking at Nancy. She's,
We're getting some.
oh, she's, are you busy? It's okay.
Oh, no, I was kind of zoning out.
Yeah, Nancy. So Nancy, the question was like, while the raster is building, let's say that I'm running a session with a class. While the raster is building, what might my students be doing?
That's a good question. We're still working on developing our solar sessions. So far, what we've been doing is doing some presentations, different solar information. There's a lot of different levels of solar observing. So you can start out with just, you know, looking at the pretty picture, and then you can go all the way up to making the maps. So if you're into Python and coding, we could use your help with developing that part of it. It's on our website. There's five or six steps that need to be done. We have 3 of them done. Thank you to one of our students in India. And so we need to have that continued. So
we have 2 more students from India who are ready to jump in and help.
yeah.
So they're already
like
reaching
Manis
out.
and-
Oh, Manis is one of them.
Yeah.
Yeah.
I've been talking with him online.
Oh, you have? Okay, so Manis is also part of the Eclipse project, and Brian just introduced us to that, made that introduction. So I've been trying to shout out Manis to see if might want to unmute. Okay, so you've been working with Manis already?
Just conversations.
Just
not really working.
conversations, okay.
Yeah, and then who else is?
Sarthik?
Okay, yeah.
Have you met Sarthik yet?
Yeah, we had a lot of interest from the solar citizen science program.
And so I know I'm saying it wrong.
I don't know that one.
Okay. So
Anyhow, yeah, so we'll just keep information going as we get these developed. And we've also did a lot of software changes. So what used to be an hour and 10-minute scan, we can do now in a lot quicker time, like 13 minutes. So that really decreases the amount of time we need for sessions and stuff. So that's going to totally change up what direction we were going before. So we're gonna have to rethink that whole thing.
Yeah, I can see that might really allow for different, you know, groups, differentiated groups. So like if you wanted to break your, whether it's after school program or a scouts program or a classroom, whatever, maybe you could break them up into different groups and then kind of cycle through. That might allow some different things like that than a longer scan would allow for. So again, GAVRT's really collaborative. So we're constantly evolving and working to try to create different opportunities for our participants. And so that's a very two-way street. We want to see what your needs are so that we can adapt to meet them and meet you wherever you're at, and then also see what would be beneficial, and then either have some of you guys, like we've talked about, do a special project that helps us develop one of these tools, or just to pilot some things with your group. Like, you know, a lot of times we're doing testing, so to help us with some beta testing as we roll out new aspects of a different campaign, like solar.
I'm very excited about the way this raster scan is pulling up.
Yeah,
That's really
yeah, it looks
neat.
good.
I know at first we're sort
Crescent
of
sun,
seeing a full sun on the raster scan. That it's like, what's wrong? Why isn't it working?
But it
It's
is
because
working.
of the moon
The
shadow.
moon is
Yeah.
doing its job with this
Yeah.
experiment.
I go take some snap.
Okay.
One active region that you can still see on
Yes.
the crescent that's
Yes,
visible.
yes.
So that was that the one that we were just looking at on HelioViewer? Is it the same active region?
That's a good question. I think it might be actually, yeah, the first one that we
The
targeted.
first one?
Yeah.
Okay, so going back to the first one
Yeah.
as we move across. It's very cool. Yeah. I don't know if you guys heard, but Marin first said crescent moon, because that's what,
That's what I was just saying.
You always say those two words go together, and Bailey was quick to say, no, crescent sun.
Crescent.
can't make a mistake in front of Elu.
No, that's that science talk, like I talked about. Us teachers were a little bit more like whatever, but scientists, you don't let each other off for anything. Love it. All right.
It's really cool to picture the moon and taking the bite out of the sun there.
Yeah.
And space is so big, and we're just happen to be witnessing the moon and the sun line up with each other.
That's so cool.
It happens all the time in the universe, but we're here
From our perspective.
to see it. Yeah.
Yeah.
Yeah,
It doesn't happen all the time from our perspective.
no.
Yeah. So we will definitely be looking at these images, doing some processing of the images. And I could for sure see, all of this will be going into eventually the paper that we publish with results.
Yeah.
And we want you to participate, like has been shared recently.
Yay.
While we're waiting, wait. Will the images also be available online? Yes, they will. And as we, on our solar, I guess we should show that, our website. We'll show that in a little bit, but yes, we will put these images on our website. So if you go to GAVRT.org, you can look by each campaign. So if you go into solar, you can see some of the maps that we have created previously. And of course, these will be on there. And then as they continue to be processed and the data is analyzed.
Yes,
So
So we got emails this morning, so Becky sent us emails of what it should like, and it's cool to see the comparison of the actual radio to go.
Oh, yeah.
Oh,
it's just
nice.
like that.
okay, yes, I do have
So
them.
look for slide 5.
Thank you for telling me because I was going to start with slide
All
1.
of them.
Oh, yeah.
Okay.
I'm gonna make you presenter again. So you can.
Okay. Oh, where did I go? Okay. Show my screen. Let's try this. Where did it go? Where did you go? I had an image. You just see my school.
We are in that building right now.
Anyway, I'm going to pause that for a second and I'm going to find it because I don't know where it So when we were talking about you computer science folks and how useful you are to our lives.
Yes, for sure.
Hang on a second. I promise I'm going to.
Not computer science, the lack of sleep, I'm sure we all have.
yeah,
Right?
okay.
It's starting to hit.
So let's see. So here we go.
Yes.
So let's look at this. So Ryan, what are we looking at here?
Those are rasters from yesterday, showing the active regions and things throughout the day. Slide 5 is particularly interesting because it shows a magnetogram image. Do you have slide 5?
I thought that was slide 5.
No, slide 5 was a.
Okay. So hang on a second. I'm going to go back
previous slide.
the previous one. So that was slide
Oh, what
5,
Slide 3.
slide 3,
I'm so tired.
slide 3.
The
It was an
dyslexia
odd
is
number.
Kicking in and it's all flipping.
Okay, so hang on. Let me just.
Slide 3 right down there.
Yeah, okay. All right, we're gonna try that. Okay. Ooh, okay, let's look at slide
There we
3.
go. Babe,
Okay.
You want to talk about that slide?
Yeah.
Rayla, would you like to come in?
Come in. I'm actually gonna go get my glasses.
What we are seeing now is the moon is moving out, because slowly it is revealing the parts which was covered. So that is what the pink circles show. And you saw the image which looked like a crescent moon. That is the sun part which is we can see, because the rest of it is covered by the moon. Now, as the moon is moving from top right to top lower bottom, so as you see, each circle is moving down, and so it will start revealing portions of it. So the active region AR 13462, which is now behind the moon, but it will slowly start coming out of behind the moon, from behind the moon. So we will record that signal to see what kind of a structure we can recover about that. Okay, so we will do the same one about the another active region, which is 13465. the black circle towards the left corner. And finally, at the limb, which will be happen, the last one we will do. That will be the last contact. So we observe the first contact and we will observe the last contact also, this point. And so I hope I made it clear.
It's exciting. This is exciting to see it happening real time.
Yeah. Okay. So far, so good.
So far, so good. Thank you.
Thanks, Belu. All right. Very exciting.
So I was trying to figure out where we are. When is the maximum?
Oh, like when is the maximum coverage?
Yeah, of our fund, 80%. Let me take a screenshot of my timing.
It should be right about now, I think.
Was it the neutrino detectors? Neutrino detectors would be one big story some years ago.
My parents went out and made your pinhole camera.
Oh, fun. Did it work for them?
It did, yeah.
Nice,
There's
good.
the Eclipse.
Excellent. Good, good.
To show all you out there. This is you can view with your pinhole camera just like this.
I have a family in Arizona also who sent a picture that they did that as well. And she got a really good image as well. Let's see that.
Oh, that's cool.
Piece of paper, and it was just a normal piece of paper.
Yeah.
She sent a picture of the paper. This is the paper that I used. It was normal school paper, and you can create an Eclipse viewer.
Yeah, or if you're retro like my parents, you can use an old punch card, if anyone remembers what those are.
Nice.
Belu and I were talking about punch cards on the drive here this morning.
What's that?
I mean, the
My
old
parents
punch
use the punch cards to make
time
their
cards.
pinhole camera.
Some of us started that way.
I used to carry a deck of cards sticking out of my pocket all the time.
Yeah, now you just carry this brick all the
Somebody
time.
notes and all that was going in the card.
Yeah.
Well, maybe while we're waiting, I can talk a little bit about science that has been done previously with
Oh,
eclipses.
that would be amazing.
Maybe Ryan, if you can send the screen share back over to my laptop.
Do you want to switch places?
Sure, yeah.
Let's do that.
Do a little
Switch over.
musical chairs here.
You are presenter again.
All right, cool. All right. So, I'm taking this slide here. There we go. All right. Interesting, but it's not resizing. Maybe I'll do this. Just
There
so
you go.
can see all of it. I'm not sure why it's cutting off. Oh, actually, no, it's fine here. Okay. Technical difficulties. All right. So, it's just some science that has previously been done with solar eclipses. So back at the beginning of the 20th century, when Einstein was coming up with this theory of general relativity, which was basically a way of describing the force of gravity as a deformation in space and time. So if you picture space-time like the surface of a trampoline, and you stick a ball in it that's heavy, like a bowling ball, it'll deform the trampoline. Yeah, you'll get like a deformation.
Concave,
Yeah, a concave feature in your trampoline. And that's what Einstein was proposing you could describe gravity as. Basically, you picture space-time, you stick a mass like the sun into it, and it will deform space-time, just like that bowling ball would deform the surface of a trampoline. So he was proposing this theory of general relativity. And one of the ways that he said it could be demonstrated was that during an eclipse, when the sun is dark enough, when it's being obscured by the moon, that you could see background stars. One of the things that you would observe, if the theory of general relativity is correct, is that you would see a deflection in starlight that happens when the light from a background star is bending around the sun. And you can kind of think of it like if you took like a ping pong ball and you slid it across the surface of that trampoline. Normally it would just go in a straight line, but if you have that bowling ball there, it would kind of deflect around.
Yeah.
It would alter the path. So the same thing with starlight being altered by the mass of the sun deforming space-time. And so he predicted that you would see an offset in the position of background stars during a total solar eclipse due to general relativity. And he was proven right when Sir Arthur Eddington, who's a British astronomer, observed the solar eclipse of 1919 and observed that offset in position of background stars behind the sun during a total solar eclipse. And the amount of the position offset was just what Einstein predicted it would be. And it was a demonstration, one of the first demonstrations of the validity of the theory of general relativity.
That's amazing.
Yeah, super cool. So we know that GR is a pretty good description of gravity and forces. We now have much better tests of GR in the form of much more massive objects like supermassive black holes. So scientists are testing the limits and the validity of general relativity around supermassive black holes. So we don't use eclipse observations to do that kind of verification anymore, but eclipses are still really useful for different kinds of science.
Yeah.
So this next slide that I have here is a demonstration of just what we can do during a total solar eclipse. So we've been talking a lot about the corona, which again, if you're just joining us, is that tenuous plasma that surrounds the sun. We can refer to it as the solar atmosphere, basically. It's a plasma that's heated up to millions of degrees Kelvin and is where the source of a lot of magnetic activity on the sun. So where you can generate things like coronal mass ejections, which are explosions of plasma off the surface of the sun. You can generate things like flares, which are really bright electromagnetic radiation events. A lot of exciting things happening in the corona.
Yeah.
But you normally can't access the corona when you're observing the sun because the sun is too bright.
Too bright.
So you never see it. And we never see it here on Earth, except during periods of a solar eclipse.
A total solar eclipse.
During a total solar eclipse, yes. Important point.
Yes.
That you need the moon to be fully obscuring the disk of the sun to see that corona. And what I'm showing here is sort of a composite image. So in the center, I have an image of the surface of the sun, the photosphere. I believe this is at ultraviolet wavelengths. This middle area, which is kind of gray colored, is a view of the corona that you would get during only a total solar eclipse. And then the outer part of this image is also an image of the corona, but at much larger heights, much further out in the atmosphere of the sun. And this is the region that you can access from space. Now, the reason you can't access this inner region of the corona from space is because the way most spacecraft observe the sun is they have something called a coronagraph. And that's basically just something that's obscuring the disk of the sun, just like how the moon obscures the disk of the sun during an eclipse. But it's sort of like a manufactured eclipse that we create so that we can observe this outer structure. But the coronagraphs cover a much larger area than just the surface of the sun. And so what's accessible from space is really only this very outer region. You really need to observe the sun from the path of totality with your optical telescope, whatever, to access this inner portion of the corona. And this inner portion of the corona is where all the exciting stuff has happened. That's where we think the magnetic fields, which you can see represented by the lines in this image. There's a lot of structure in the corona that you can see from this in the central part of this image. That all represents plasma that's tied up in the magnetic field lines of the sun's atmosphere. So you can see a lot of structure in the magnetic fields in this part of the sun's atmosphere. We think that those magnetic fields are heating up and powering basically the corona. That's why it's millions of degrees Kelvin, we think, because the magnetic field is supplying all of the energy to heat the plasma in the sun's atmosphere. And we can only see the physics that's happening in this region during periods of total solar eclipses.
Which makes them very special.
Yes, indeed.
That's why so many people get excited when we have a total eclipse coming.
Yes. in addition to the cool factor, it's also really useful for science.
Well, and it is so interesting that within the space of a few months, October and then again in April, we have the opportunity to do these studies with
Yes. Yes.
with a eclipse, total annular and then a total eclipse.
Yeah, yeah,
So-
exactly. And this will be, so April 8th, 2024 is when we have the total solar eclipse crossing the US. After that total solar eclipse, there won't be another total solar eclipse viewable from the United States until 2044, I believe.
Wow.
So, you should take advantage of this one and view this one.
Don't miss it.
Yes, indeed. So here's just another really cool image. This was also taken during a total solar eclipse. I believe this was the 2017 eclipse that passed through North America.
That is a really neat image.
It is, it's super cool. So this is a false color image. So there's three things represented here. The white part of the image represents basically white light. You can picture that as just total intensity, all the flux that you're getting in optical from the corona. You can see a lot of structure. This is a really high resolution image. You can see a lot of structure in the corona. You can see these magnetic field lines coming up from the poles of the sun. And you can see magnetic field lines that are not going out into the atmosphere.
They are those prominences that we're seeing.
Yes, yeah. We're seeing prominences coming from the surface, mostly in the sort of like mid-latitude regions. And then there's two other colors in here. There's green and there's red. And both of those colors represent different transitions in iron.
Wow.
So you're seeing iron lines in the corona of the sun.
It's amazing to me how different minerals and elements will reflect a different color.
Yes, yeah. Yeah, so each of these colors represents a specific transition for iron in the atmosphere, and they correlate to temperature. So green is representing one temperature plasma in the corona, and red is representing another color. And I'm going to get this backwards. I think green is representing hotter temperatures in the corona, and red is representing cooler temperatures in the corona.
Very neat.
Yeah. And then we have our own GAVRT observations.
Oh, there's Nancy.
Yes, so here's Miss Nancy. She's sitting over there right now observing.
She's running the computers.
Running the observations, making sure everything actually happens, that we actually collect our data. But yeah, so this is, so we typically run GAVRT with students, citizen scientists as well. Erica is also one of our operators. Who makes sure the telescope runs and that things go as planned. And this is our telescope right here. This is DSS 28, is that right?
Yes, you can tell by the pedestal on the bottom.
Oh yeah.
Yeah.
That's an older feature, is that right? Like the newer ones don't?
Yeah, the new ones are sunk where the control room and everything is sunk into the ground and you use a tunnel to get into it. This one, everything is above ground.
Oh, cool.
So,
I didn't know that.
oh, that's
Oh, this
14?
is DSS 14?
Oh, okay, that's 14.
Oh yeah, it's big, 70 meter.
I think a cool pic from Sandy too, to put the size of DSS 14 in context.
Oh, okay.
That should be in your inbox.
In my inbox, okay. I'm going to stop sharing right now so I can pull this up.
Let's see if we can find that. Oh, okay.
Oh, yes.
I love this
I love
picture.
this picture too. All right, so this is cool. And I know that NASA likes to share this image on social media,
Yes.
like around like the Rose Bowl game. And I think this is actually a picture of the Rose Bowl, is that right?
Is that the Rose Bowl?
Okay, so this is the Rose Bowl in Pasadena, and then to scale is DSS 14, which is the 70 meter antenna at Goldstone.
It was plopped right in the, what is that, the 40-yard line?
Yeah,
Looks like it.
So just to give you a sense of how big these radio dishes are that we were talking about.
Mhm.
So the one that we're observing with today is a little bit smaller. It's a 32 meter antenna.
I've heard it described as if it was sitting on a baseball diamond, it would be the infield.
Oh, okay.
So another good scale to size. Maybe we can have our NASA people put one of those together.
Yeah, we can make that ourselves. Yeah, and then show it during like the World Series or something. I don't know.
That would be fun.
But yeah, so just to give you a sense of, this is the kind of thing that we're observing right now, using right now to observe the sun.
Yeah. Remotely, we're not even there.
Yes, yeah. That's the nice feature about telescopes nowadays. In particular, radio telescopes are like this. you can usually observe remotely.
Yes.
And the cool thing about radio telescopes is you can observe during the day, unlike optical telescopes, which is how we're observing the sun right now, during the day.
Well, but at nighttime, any celestial objects that are up in the sky, we can point at.
Yes.
So we don't need to have the light of the sun to be able to study anything out in space with the radio telescopes. We can, whenever it goes into, what is that? I'm thinking of the little, on our sheet, you can see the rise and the set of it. So as long as it's up in the rise and set, we can track it. So
Yeah, so we can observe 24 hours a day, and it's just a matter of what targets are above sky for us to look at.
radio galaxies, we observe the black holes. We have a list of different black holes that we're studying. We of course use the radio galaxies as a calibrator source because we know what those readings should be coming off of those. So that helps us when we're doing a reading of an object like a black hole that we really don't know that much about to get the true readings or the flux density of those black holes, because we know how much our calibrator is. And so we'll run a scan on a calibrator, then we run a scan on the object, usually a black hole, and then we run another calibrator scan so that we can make sure that the readings we're getting are true, true readings. So
Very cool.
how's it going over there? I'm hearing happy laughter.
We're just laughing at how.
Maybe last time I took page one. You know, you call me every day.
Well, maybe that's a good segue to talk about different GAVRT programs. I heard Lisa talking about the 4 different programs that we have earlier.
To touch on them earlier, we have the Solar Patrol, which is part of what we're doing right now, scanning the sun. Oh, I love that. Look at that. That's beautiful.
Yeah, nice visual image.
Nice visual. Jupiter Quest, Solar Patrol. We have the Black Hole Patrol and SETI, which is techno signatures on there. That is the search for extraterrestrial intelligence.
Yes,
So
that one's always fun.
maybe looking instead of extraterrestrial intelligence, looking more as techno signatures now. So something that is going to repeat coming to us from a specific point out in space. Space is full of random noise. So we're always picking up signals here and there, different signals, different intensities. We're looking for the techno signatures. If it's something that is coming from a specific point over and over and over again, then we know it's probably something that's more technology driven, not necessarily just random noise that's happening in space. So those are the signatures that we're looking for with the techno signatures with our SETI program.
Yeah, it's very cool. And it's kind of informed by what we produce.
Yes.
So the radio frequency emission that we humans have been producing since we became a technological civilization, worldwide civilization at the beginning of the 20th century.
Exactly. And it's always interesting to me when we do scans. So if the elevation is lower towards the horizon, we pick up a lot of noise from the Earth. So everything from cell phone signals, television signals, radio, microwave, all of that contributes to the noise coming into the sun. And as the elevation of that dish points up away from the horizon, the noise levels drop significantly. So it's really interesting to see the correlation of how noisy the Earth is in general versus how when you're staring up into blank space, it gets very, very quiet. So, and I think that's one of the reasons why these dishes, the things that we're looking for and listening for, they're tiny, tiny little signals. It's not like somebody walking through the room with a symbol. It's these little tiny signals that we're locking onto and gathering information from.
Yeah, I actually have a really nice plot that describes, that shows what you're describing really nicely, Erica.
I'm jumping all over the place. You probably have this all laid out and beautiful.
No, it's perfect. It's organic. I love it. So this plot over here on the right is basically a visual representation of what you're describing. So, and actually there's another plot here that I didn't include that would go above here. So what you're looking at is something called a waterfall plot. It's also referred to as a dynamic spectrum. And it's basically a spectrum from a location on the sky as a function of time. So each of these rows in this plot describe a certain frequency, observing frequency on the sky. And then each of these columns represents a different time. So you can think of us building up this dynamic spectrum of this waterfall plot, right? Slowly building up spectra line by line. So as a function of time, we have more and more spectra, and we compile them all into this waterfall plot. And what you're not seeing here is all of that human-generated interference.
RFI.
Radio frequency interference, which is the bane of any radio astronomer. We humans produce so much radio emission, and it's so bright.
Yeah.
In order to view anything that's happening outside of Earth in either our solar system or further out in space, if we're looking at supermassive black holes, we have to be able to avoid that RFI. Otherwise, all we see is the RFI. It's basically like trying to look at something really faint when you're in a really bright room. You can't see it because you're swamped by all of that noise from that bright light source. So what we do is we excise or we remove the human-made RFI, and that's what's happened in this plot here. So these black vertical stripes represent parts of the data that we selected and removed because it was full of really bright human-generated radio frequency interference. And what's left is a lot of fainter structure that now you can see when you've removed that RFI. And then we can zoom in to this tiny part of this plot here. If you zoom in on this cutout, you can see there's like 1 pixel in this dynamic spectrum that looks brighter than the rest. And that's what this bottom plot is here. So we've zoomed into this cutout, and you see just a single tiny bit of emission at this precise frequency that's only about 1 hertz wide, which is extremely narrow, and at
About a second long, it looks like.
Yeah.
Maybe even a little bit less than that.
Yes, and the fact that it only lasts for a small amount of time means that it's coming from a particular location on the sky, right? And that's just due to the way that the telescope is observing. So our observing strategy with SETI is to try to target as many potential planetary systems as possible.
As we can, we take as many sources. So we have files and files and files that need to be analyzed. And what we're hoping to find is files taken at different times, different years even. And we're hoping to find that little white line in the exact same point, and then it's repeated. So what's what we're looking for is something that's not random. Once it's repeated, it starts to become, now we got to look and see how often does it repeat? Is it something that we truly are getting a signal, or is it still just maybe a random noise? So
Yes, yeah,
very layman's terms.
yes, yeah. And we're targeting signals in particular that are extremely what we call narrow band, or they're not produced over a really wide frequency range. And that's just because, you know, natural astrophysical emission that we normally detect is inherently very broadband, or it covers a really wide frequency range. It has to be something manufactured, artificial, to be this narrow in frequency. This emission, this bit of emission that we're looking at here is only about 1.5 hertz wide.
Little blip.
Yeah, you wouldn't expect that naturally to be occurring in nature, so we try to use that as an indicator that, oh, maybe there's some sort of civilization that's
Sending out
producing
some
this
kind of a
technology.
signal.
Yeah.
We call that a candidate.
Yes, and we have lots of candidates and no confirmed detections. So
Correct.
as of right now, we are the only confirmed species that we know of.
That sends out the radio signals like we do.
That's right. But we keep looking,
Always.
just in case.
Because we are a curious species.
Yes.
And we want one of our participants to spot it.
Oh, that would be amazing.
Yes, that would
wouldn't
be
it?
very, very cool.
We actually have a publication that's going through the peer review process right now on SETI. And so
Nice.
more than 200 students, I think, participated in that particular paper.
Yeah.
And they looked at plots just like what we're looking at here. And they picked out themselves manually these kinds of candidates that Eric was just talking about, these very narrow band signals at particular times corresponding to particular target stars, and noted those as potential SETI candidates. And that's all been compiled into a paper. And we didn't detect any SETI, but we have a really nice statistical sample of many hours of these kinds of dynamic
It's
spectra.
amazing. It's amazing.
Yeah. Yay. We can also talk a little bit about, maybe I'll start at the top here. I'll go back to Jupiter Quest. So this is a campaign where we're particularly observing Jupiter in coordination with the Juno spacecraft. And this is to target the high energy electrons that are in something called the Jovian radiation belts. So Jupiter has a belt like around its middle, just as you might guess from the name, of really high energy electrons. And that belt of high energy electrons produces really bright synchrotron emission. So if you had tuned in, we talked about it probably an hour ago now. I don't know. I have no concept of time anymore.
I'm with you on that right now.
We talked about gyrosynchrotron emission that happens on the sun, and that's actually what we're trying to observe right now with our GAVRT telescope during the eclipse. A similar kind of emission happens on Jupiter, and it's called synchrotron emission rather than gyrosynchrotron emission. This similar concept where you have really high energy electrons gyrating around a magnetic field, and when you accelerate an electric charge, you produce electromagnetic radiation, and we call it synchrotron radiation. In this case, it's not gyrosynchrotron, it's just synchrotron, and that's because the electrons are moving very relativistically, close to the speed of light, and so you produce extremely high energy radio emission at gigahertz frequencies, and we can observe that with our GAVRT telescope. This program in particular is really well suited for the classroom setting. So targeting Jupiter when it's up during classroom times, during the day, and letting the students operate the telescope with you and Nancy and collect data on Jupiter.
Yeah, and we do have a whole season basically for when Jupiter rise sets are available to us. So the Jupiter quest is not something that we do every day of the year. It's something that's only available at certain times because, of course, like you mentioned, it has to be up. So we have to be able to see it, to be able to scan it. So.
Yes, we can't observe through the ground.
Right.
Yeah.
Or the moon, as we're learning today.
Yeah, we can't observe through the moon, which is how we get eclipses. Super cool. Yeah, so here's just a kind of diagram of those belts that I was talking about. So here's a little cartoon of Jupiter, and then these contour maps that we're looking at here, these are these multicolored red, yellow, green, purple contours on this plot represent, this is actual data. These are measurements of Jupiter's synchrotron radiation belts taken at gigahertz frequencies. And just as the name described, it's a belt, a torus of high energy particles that surround Jupiter. And a lot of these particles are produced by actually a moon of Jupiter. So one of Jupiter's moons, the one that's closest to it, I think, is called Io. And it's actually really volcanic. It's the most volcanic object in the solar system, actually.
Oh, interesting.
It's basically a tiny rock that's just full of volcanoes. And that's because of something called tidal forces. So the gravity from Jupiter and also the gravity from the other moons of Jupiter are basically constantly deforming Io, that moon of Jupiter. It's kind of mushing it around. And if you picture mushing around a rocky body, that creates a lot of friction, and that friction heats the interior of Io, and that's what creates all that volcanism.
That's amazingly interesting.
Yeah.
I love that.
So in addition to producing a bunch of cool volcanoes, it also spews a lot of charged particles out from the moon of Io and into the belts of Jupiter. So that's what creates the synchrotron radiation belts. And we're interested in studying those because we want to know how they interact with the magnetic field of Jupiter and produce that really bright synchrotron radiation that we were talking about. So another thing that interacts with that synchrotron radiation belt is high energy particles produced from the sun, which is something we call the solar wind.
Nice.
So you can picture it as I saw it phrased once, and I really liked this phrase, a breeze of subatomic particles coming off the sun. So if you picture electrons and protons that are being carried off the surface of the sun from those open magnetic field lines that we were looking at earlier when we were looking at images of the corona, those high energy particles are streaming off the sun and interacting with everything else in the solar system, including objects like Earth and objects like Jupiter. So Jupiter has a really strong magnetic field. It has the strongest magnetic field in the solar system, if you don't include the sun. And that magnetic field creates a cavity around Jupiter. And that cavity created by that magnetic field is what we call the magnetosphere. So these charged particles in the radiation belts are getting trapped in that magnetosphere and interacting with the solar wind. And observing Jupiter's synchrotron radiation is a way of probing that interaction between the solar wind and the magnetic field. So yeah, super cool. That's what this image on the bottom is showing. Here's a sort of cartoon image of what the magnetosphere would look like. You can see the yellow lines representing the solar wind particles hitting that magnetosphere and getting deflected around it.
Very similar to how it happens here on Earth.
Yes, exactly, yeah. And we think that possibly having a magnetic field is actually really important to fostering life. So it's likely that Earth's magnetic field played a really important role in retaining the atmosphere of Earth. Mars is sort of the counterexample to that. So Mars has a very thin, tenuous atmosphere. We think it once had liquid water on its surface, but it doesn't any longer. And part of the reason for that is that Mars does not have a strong dipolar magnetic field like we do. And so basically all those high energy particles in the solar wind, and also coming from things like coronal mass ejections, which we talked about earlier, would hit Mars's atmosphere and strip it away completely.
Yeah.
So because Earth has a magnetosphere just like Jupiter, you can picture if Earth was here in the center, you can see similar magnetic field lines, and you'd see this nice magnetosphere shielding Earth and allowing us to retain our atmosphere. And so when we're looking for life on other exoplanets, now maybe not technosignature life, but just microbes, very basic life forms, or even just looking for planets where habitability is a possibility. We want to look for planets that we think have a strong magnetic field for that very reason. So yeah, that's Jupiter Quest. And here's a plot of actual GAVRT data that was taken with Jupiter Quest recently. So this was a publication by a student. Yeah. What was her name?
Clara.
Clara, yes, thank you. So Clara was a student that worked on this data while she was in high school. And she was the first author on this paper that was published in 2022. This was taking GAVRT data on Jupiter from prior observations. These were observations on the left taken by Belu, who's sitting over there at our control desk, and then observations that were taken by Clara with GAVRT. And what we're looking at here is a plot of the flux density of that Jupiter synchrotron radiation belt as a function of time. So going back all the way to 2016 until 2022. So the GAVRT data are these points here in the plot with error bars. And the solid black line is basically a simulation. What theorists who are modeling the Jovian system would predict the flux of the Jupiter radiation belts would be based on the solar wind, basically. So there was a theory that the flux you expect from the synchrotron radiation belts is a function of the amount of solar wind material, the amount of those protons and electrons hitting the belts themselves. And you would expect during periods of high solar activity, so when it's at the peak of its 11-year magnetic activity cycle, when you're producing a lot more energetic phenomena from the surface of the sun, including a higher solar wind pressure, you would expect more emission from Jupiter's radiation belts. And that's exactly what we're seeing. So there was a peak back in 2017 and 2018, and then a minimum more recently in 2020 and 2022.
So is it an 11-year cycle on Jupiter as well?
So yes, you would see this go at an 11-year cycle. An interesting fact, though, is that it's delayed from the solar cycle. So you would see a peak in the solar cycle, and then about 2 years later, you would see a peak in the Jupiter cycle. And that just has to do with how energy is transported once it reaches the Jovian system, the source of the high energy particles and all that. But there is that 2-year delay, but you do see the same peak and trough cycle, just at a slight offset from what you see from the sun. So really exciting GAVRT data that helps demonstrate that these simulations, which are represented by this solid curve here, are consistent with what we see observationally in the GAVRT observations.
Yay, Clara.
Yeah, so awesome job, Clara. And you out there can participate in science just like this by contacting us and getting to work with the data to take the observations yourself, and then also reduce the data, turn it into science data products, interpret that science, and contribute to scientific body of knowledge by publishing a paper. Just like
And to be a first author on a scientific publication is, as a high school student, is no small feat.
No,
Right.
Yeah, that is a really big deal. To be named at all is really important and would be a very rare opportunity for a high school student or an undergrad student.
Yes. Yeah.
Or a citizen scientist at all. Right?
Yeah.
That's a goal of ours.
Lisa, do you want to jump in and look at if there are any questions?
Sure. I don't think there are, though. I don't think we have any questions, but I do see some new participants who have joined. And I can read your names now because I went and got my glasses.
She's got a question from Aaron here in Apple Valley.
Aaron. Hi, Aaron. Does this type of eclipse give NASA a better opportunity to view the dark side of the moon and its features?
Oh, that's an interesting question. Yeah, so there's not too much lunar science that can be done during an eclipse. Scientists are mostly interested in solar science that you can do with the corona during an eclipse, as we were talking about, or in our case with the radio observations, monitoring active regions, getting really high angular resolution observations. The interesting features on the moon that are relevant during an eclipse is that the moon's limb isn't a perfectly smooth surface. There's mountains and valleys and ridges on the moon, and those play an important role in determining what you see during an eclipse. So you might have heard of something called Bailey's beads, or even the diamond ring effect during a total solar eclipse. That's basically what happens when the moon is starting to cover the sun, and when it gets to the point where you're nearing totality, but not quite at totality, you'll get more sunlight coming through those ridges or valleys on the surface of the moon. And it creates bright spots along the ring of the sun, the remaining sun that's viewable. And those are called Bailey's beads, named after an astronomer named Bailey. I can't remember his first name. And then the diamond ring effect is when you get almost complete totality and all that's left is a single really bright spot.
Just one.
Just one. And it looks like a diamond ring. That's
I bet you. That's the kind of diamond ring we want also, as opposed to the annular, which is a ring
of fire, yes.
Ring of fire all the way around. I do see that Sage Gruber has joined us. Sage is has a previous space science student at Norton Science and Language Academy. We also have Cynthia, who is the longest current employee of the Lewis Center. And so she is special in many ways, but has seen everything about the Lewis Center develop over time. And so exciting to see those of you who are joining us midway through, and those who have been sticking with us all the way from the beginning. So we have a few diehards who have stayed with us in the beginning. And I definitely understand, like us, you guys are going outside to view and then coming back in. And so again, we just want to be as interactive as possible. Did you see that comment to you when you were showing the Rose Bowl?
Oh, nice. It's a cool image. I'm glad to share it.
So any questions? Sage, do you have any questions for us? Should we go back to Belu and Nancy? Should we have you guys share?
We're giving you a eclipse right now. It's showing up.
Why don't we,
Very slow.
and then we can go back to other GAVRT campaigns. Let's see what we're seeing. We're going to switch our view. All right. Okay, so this is what the GAVRT team is observing now.
Yeah, so we were down at about 10 kilohertz, and we're slowly going up as the moon is egressing from the sun.
Cool. Yeah, so you couldn't hear Ryan there. He's describing the fact that we're coming out of egress now. So the moon is leaving the active region that we're targeting. So we're seeing an increase in flux as more and more of the active region gets exposed and the moon moves more and more away from our field of view. So we're increasing in flux here. That's what the red line is showing as a function of time. So there's the UTC time, universal time, shown on the x-axis here. So we're at about 1716 UTC, which is 1016 here local time in California.
Yeah, we have about what, maybe 45 minutes left.
Yeah, we're almost out of the eclipse.
We're
here.
almost out the whole window. It's been
wow.
exciting though.
It has, yeah.
Yeah. What questions do you guys have, or what are you maybe seeing in your area? Or I can say I stepped out for a little while and our basketball team was practicing, our basketball teams were practicing. And so I was able to take the Eclipse glasses out as some kids were getting dropped off. And it was really fun to just have them view. A lot of people maybe didn't even realize there was an eclipse today and weren't quite connecting that it feels just a little bit different outside, right? That everything looks and feels different, like Marin was saying earlier in our broadcast. And so that was really fun to get our coaches out there and our students and have them go, oh wait, there's more than basketball practice going on today. There's this really cool solar eclipse. And so I'm grateful to our coaches for letting me interrupt practice and for the parents who got out of the car because I was very excited to show them. Yeah. That was fun. So we'd love to hear a little bit about what's going on in your area. Oh, when is it safe to put away our Eclipse glasses?
Oh, that's a good question.
Yeah.
So today, during today's eclipse, it's never safe to put away your eclipse glasses.
Yeah.
You always want, whenever you look at the sun, you always want to have these with you. You want to look through them at the sun. And you can use them any time of year. Like if you just want to, tomorrow you want to take a look at what the sun looks like. I encourage you to, if you have eclipse glasses, to put these on and go look at the sun.
Yeah.
I always think it's cool to look
I
at the
think
sun.
it's cool too.
So yeah, you always want to view the sun with these on. You can damage your retina. You can do damage to your eyes if you look at the sun.
So why is it even more risky to look directly at the sun during an eclipse? We
Yes.
talked about that earlier, but we haven't talked about it in a while.
Yes, yeah, that's a good question. So it's more dangerous because it's a lot dimmer outside when the eclipse is happening, especially if you're near totality or near the path of annularity in today's case. It's so much dimmer outside. And so what happens is your eyes dilate to let in more light because it's so dark. And you dilate your eyes, you're letting in so many more dangerous ultraviolet, infrared, and optical photons that can really damage your retina. So it's really critical, especially during an eclipse, to view the eclipse either with a pinhole camera like we were showing earlier.
I don't know where our pinhole camera went away.
Here's our pinhole camera.
Yeah.
It's very high tech. It's a sheet of paper with a hole in it. But it's a really excellent way to view the eclipse if you don't have a pair of glasses. You would just line this paper up and then you would look down at the shadow that the pinhole camera that your paper creates, and you would see the eclipse happening. You'd see the crescent shape of the sun in the shadow of your pinhole camera. During a total solar eclipse, I do want to say if you're in the path of totality, that you should take these off. Only during the moments of totality.
Yeah.
If you don't have these, if you don't take these off, you won't see the corona, which is really the spectacular part during a total solar eclipse.
Yeah, it is such a, I just really have to say, check your travel agenda for April.
Yes.
Yeah, I think maybe Marin and I will be,
Flying to Texas.
yeah, we'll be correspondents like Eileen is today. We're going to be the GAVRT correspondents from Texas, along with Steve and whoever else wants to join us. That would be the dream. So, anything? Oh, there's a big.
Oh,
yeah.
Drop down to almost zero flux here on our plot.
So we've now moved over to.
You want to come over so they can hear you?
465, so that we can test the next active region being uncovered by the moon.
Okay, yeah. So what Ryan is describing is that at this point where you see a steep drop off in the flux in our plot here, represents when they moved the pointing of the antenna. So they move the antenna to point at a particular location in the sky that's still being obscured by the moon. So they're waiting for this active region that we targeted earlier to be visible as the moon passes out of the field of view of the telescope, slowly revealing the active region underneath. So we should see slowly, as time goes by, the flux in this active region that we're pointing at increase. So you'll see this line go up and up and up, representing more and more of the active region being revealed as the moon moves away. And we call that process egress, as opposed to ingress. That's what we were looking at earlier.
Yeah.
Once this active region is completed, the last thing we'll go to the east limb of the sun. There's no specific active region or anything like that. We're just gonna blind point and hopefully we'll get some data.
Okay, cool. Yeah. Dr. Bailu, how are you feeling?
Tired.
Yes. And at the same time,
It's almost over.
and the next dream about April 4th.
Yeah.
April 8th.
Yep.
Already planning optimism.
Always looking forward. I have to say that Bailu has worked tirelessly, not only to submit the grant proposal and have it approved that has allowed us to do so much of this work, but just pouring into our kids and to us, each of us on the GAVRT team. So I think all of us really benefit from Bailu's experience and expertise. We're really, really, really lucky to have him on our team. And the fact that he got up at like 4 o'clock this morning to drive to Apple Valley when we're in is pretty amazing. And his wife made us banana bread. So you guys are really missing out.
Thank you more of it after.
Yes, you are missing out. But
Talk about the April 8th for the eclipse.
we talked a little, yeah, we've been talking about it all. We kind of sprinkling it through. Is there something in particular you want to share, or what?
No, it's nothing very spectacular for us. Actually, this had a much larger coverage than April 8th. So very partial.
Yeah.
Yeah, so what Bailu is talking about is that the fact that actually in
Oh
terms
wait,
of,
you're not sure. Ryan, can you present?
So I'm about to show a NASA solar eclipse map for 2023 and 2024, and it's going to show that here we go, that the amount of coverage of the sun is higher where we are for today's eclipse versus the total solar eclipse. So even though the eclipse that's happening today, which is an annular solar eclipse, the sun's not being totally obscured by the moon. There's actually a bit of the sun that's left during annularity called the Ring of Fire. Because we're so close here in Apple Valley with the Goldstone as well to the path of annularity, we get a lot more of a total eclipse, almost 70 or 80%.
Yeah,
80%. Oh, okay, wow, even better. Versus during the total solar eclipse that's happening in April of 2024, which is represented by this red line, or it's purple line, sorry. Yeah, we're much further away. So I think I can read off this map what percent coverage we'll get. We will only get about 37 or 40% coverage of the sun by the moon in 2024.
Yeah, that's a big difference.
Yeah, compared to the 80% today.
Yeah. So, but nonetheless, we will still collect data during that, and it will be different than the data that we collect on the daily. You know what? I don't know that we've talked about Helios figure. Have we really talked about that?
We haven't. Yeah.
Yeah, I think that that's one thing. GAVRT Solar Patrol is one citizen science project within a bunch of citizen science projects and heliophysics. And there's a reason why there's so many right now. And we've been talking about activity and that kind of thing, but let's talk about what's all the ways to get involved in the sun, maybe.
Yeah.
Sun observations.
So NASA has something going on right now called the Heliophysics Big Year. And I think it's actually a play on bird watching. So in bird watching, there's a thing called the Big Year, where bird watchers go out and try to see as many birds as possible in their big year.
Oh, I did not know that was the connection.
Yeah, yeah.
I was just in Florida and I saw a lot of bird watching.
Oh.
I decided that if I lived in Florida, I would become a bird watcher.
Oh, yeah. Well, so maybe you should do your bird watching big year and your Heliophysics.
Yeah, all at the same time. I think so.
So the idea is to have as many people, scientists and citizen scientists, viewing the sun at as many different wavelengths in the electromagnetic spectrum as possible. And it's happening now because the sun is entering the peak of its magnetic activity cycle. So as we've been talking about, the sun has an 11-year activity cycle where it goes from very little solar activity, it's a very quiet sun, to extremely active, producing tons of flares, tons of coronal mass ejections, a lot of active regions, a lot of really interesting stuff driven by magnetic activity on the sun. So that's going to happen sometime in 2025. So the Heliophysics Big Year is meant to encapsulate all of this really exciting stuff that's happening on the sun as it enters its maximum of magnetic activity. Starting with the annular eclipse today, going through the total solar eclipse in April that's passing through the US and Mexico, and then ending with the closest approach of Parker Solar Probe, which is a spacecraft that's observing the sun, orbiting the sun. It'll get extremely close to the surface of the sun, the closest any human-made thing has ever gotten, and that's touching the sun. Yes, yeah, it's touching the sun. I think that's going to happen end of December 2025.
So we think that there are so many great opportunities, and we would encourage you to anybody, just yourself, to participate in, or if you work with others and lead others, this is a great way to find out more about different projects.
Yeah, so if you go to the NASA Heliophysics Big Year website, you can look at all of the cool science that's being done with the eclipse. Let me go back in time here. So this is the Heliophysics Big Year website. If you just search NASA Eclipse or NASA Heliophysics, you can find this website. And as you scroll down the page, you can learn a lot of really cool stuff about the sun. It tells you why the Heliophysics Big Year is happening, what is it, what even is heliophysics, and how is NASA contributing. You can see a really cool picture of a solar prominence. This is an image of the corona. Those loops of plasma, which we were talking about before, That's actual plasma in the corona of the sun that's following magnetic field lines. So you can see a lot of really cool magnetic structure with these kinds of images. And you're seeing here millions of degrees plasma. So plasma that's been heated to millions of degrees, many thousands of times hotter than the actual surface of the sun itself. We keep scrolling down. There's a lot of cool links here. And I think the one that is most relevant to what we were just talking about is the heliophysics citizen science projects. So those projects that Lisa was just talking about were anyone out in the world. You just need to be a citizen of the world, which by definition is every human
Yes.
can participate in these projects. And if you click on this link here, you will see that there's a list of all the projects that you can get involved in addition to GAVRT. There's a lot of cool stuff here. I see a few that I recognize. Aurorasaurus, which allows people to identify aurora, take a picture with their own camera and submit it so scientists can analyze it. Eclipse soundscapes, so that's a fun one. If you're
So cool, yeah.
If you're in the path of totality, recording and reporting back on how wildlife in your area responds to the eclipse happening. So wildlife will think that it's suddenly nighttime, even though it's the middle of the day. Suddenly it feels like it's nighttime.
That was one of the coolest experiences from being in totality was, the sounds of wildlife, especially the birds.
Yes.
Yeah. And the temperature change.
Yes.
I think that was the other thing. And also just the tint of the light.
It feels like it's nightfall, like twilight almost, right?
Yeah, but it's just something just a little different. Even out there today, it feels just a little different. And if you're not looking for it, maybe you can miss it. But yeah, so cool. So yeah, again, lots of ways to get involved. And I think that it's important that we're just, using lots of different sources, like you said, observing from many different wavelengths, vantage points, all of that works together to help us learn more. What questions do we have as we're kind of nearing the end of our event window? Happy to keep sharing, but want to make sure that we're, how can we stay in touch with GAVRT? So that's a good question. So one way is that we are going to follow up with you, all of the participants, anybody who's participated or joined at all within this webinar. And so we'd like to get some feedback. Also, throughout the day today, we have shared with some of you who we know we really want to get involved in some special projects. And so we'll be reaching out, but also anytime at all, you can just, this email down below, you can connect with us at mc@lcer.org. That goes to the mission control at the Lewis Center, and the whole GAVRT team gets CC'd on there. And so there's all different kinds of ways. We've talked about participating, but there are also ways if you are maybe a solar system ambassador or you are a professional scientist. So we're also looking always for more people to join our team, to be a mentor, to give a presentation, giving a science talk, or maybe GAVRT might be a good fit for a proposal that you are submitting. So there is, like we said, lots of ways to work with GAVRT. So whether it's us helping you bring this really unique experience to your participants, or for you to just join us as an open citizen scientist, or for you to get involved in our team and help bring those opportunities to other people. So always going both ways. But we would love for you guys to join our mailing list too. So even if you just go on GAVRT.org on the website, there's a button to click and you can join our mailing list, and then you'll get our newsletters. Sometimes, there's a slide that we have that has pictures. So sometimes it's not only just a session. Sometimes our GAVRT group is invited to do some really cool things. So like, for example, these pictures are some examples. So sometimes our student groups have taken field trips to JPL. So we're here in Mission Control at Center of the Universe, right? In fact, Marin and Eric, actually all of us, just joined our delegation from Chile. So we had 20 students and teachers come over, GAVRT students and teachers come over from Chile, and we got to spend an entire day at JPL and Caltech, and they had a similar experience. This isn't a picture of them. This is an
another group of GAVRT students, but sometimes it opens the opportunity for that. So also, this is during the Juno launch. So some years ago, but those of you on the call or on the webinar might recognize this Dr. Bolden right here. So he was able to just stop and talk of his NASA administrator, I think one of the longest standing NASA administrators, right?
Yeah.
During 4 different presidencies or something like that. So just somebody that everybody was in awe of, and he stopped and just had a long conversation with all of the GAVRT students. These are students from all over the world and the country who were able to attend that event, and they were invited because they were GAVRT students. And then they had that really cool opportunity.
Yeah.
So, and then here's an example of Nancy working with a student, just one-on-one. This was a student who was here at the Lewis Center, and so she was guiding through a session and some data collection there. And then this is a student in the bottom center, just a student actually at the panel controlling the antenna. And then on the far right is a picture just before COVID of a training that we did. So we will hold in-person trainings, and that's an example of all the participants for the training, mostly teachers, who were able to actually go out to Goldstone and, as we say, kind of be in the shadow of the telescope, which is something that's really unique. At this time, there were no public tours of Goldstone. I think that they've opened up a little bit now. But through GAVRT, able to get some really cool opportunities to go out to cool venues, to meet amazing people like yourself and others, and then also just the hands-on. And I think I might have one more slide of other opportunities. Oh no, these are just our cute kids. Aren't they cute? These are our 2 mission controls at the Lewis Center. So we have one in Apple Valley and one in San Bernardino. These are just good model students, right? So just some of our Lewis Center ambassadors who also, and other students, they're not all ambassadors, but other students. So this is what it looks like in our mission controls here at the Lewis Center.
And over on the right, that's exactly where
Where
Ryan
we are
and
right now.
Fellow were sitting,
Yeah.
operating the telescope.
Yeah, exactly. I think, yeah, we didn't really talk about our results and publications. We have shared that we are really interested in continuing to publish, but if you wanted to get a good idea of what are some papers that have been published, you can go to that link, or to just DSN Now. It's just a really cool resource.
Yes,
So.
yeah. You can see where the DSN is pointed and what spacecraft it's communicating with. It's very
And kind of the follow the sun that we talked about earlier.
Yes,
So you
yeah.
can see when one complex passes over to another. So that's another neat thing. All right, we don't have any other questions over there at the console. How are we doing?
We're looking good. We're almost done with egress on this active region. We're now up to 424 kilohertz. So significant increase from the 20 we started at.
Okay.
nice. Should we share the operator view over
Yeah,
there?
you guys, we can go back.
Got it.
Oh, yeah.
You see the dramatic increase there.
Mm-hmm.
Yeah. So we're coming out of egress.
That's active region 13465. And then we're gonna go to the limb and watch that for a little bit, and then we'll do complete.
All right. Yeah, if you didn't hear Nancy there, she was saying once we're done observing this particular active region, which we're close to, the flux is going up and up. As the moon completely passes out of the field of view of the telescope, fully revealing the active region underneath. We're going to go to our last target, which is the east limb of the sun, and just take some observations there, and we'll see more egress as the moon's limb continues to pass out of the sun and as the eclipse ends. We're going to end here in about 20 minutes.
Yep. And then the next follow-up, we will email you all. We're hoping to have another open session like this where we look at some of the data and start the analysis process, and we want to involve you in that if you're at all interested, and also some of the other kind of deeper dive projects that we talked about as well. So we're hoping to stay in touch with all of those things, but we will have a follow-up session to this one. So today we've been just kind of looking as the data is being collected, and then there's work to be done with it for sure,
Yes.
to make it meaningful.
Yeah.
He said,
Where,
how did you see it?
where will the GAVRT antenna be pointing after the eclipse and egress?
Oh, that's a great question. So I believe the plan is to take another raster map of the sun. Observe the sun again fully rather than targeting specific active regions, create a map of the entire sun after the eclipse has ended. And then I think do some calibration observations. So we're going to point the telescope at radio sources, like calibrated sources that we know, usually something called AGN or active galactic nuclei, which are basically supermassive black holes and other galaxies that we use as calibrated sources because, as Erica was describing earlier, they're sources where we know really precisely how bright they are because we've observed them so many times over the decades.
Right.
All radio astronomers use these as calibration sources. So we're going to observe those, take some calibrator scans, and then I think we'll be done for the day. Yeah.
Yes. It's been an exciting day.
Yeah. It's been a fast 3 hours.
It has been, right? Like it felt like very early, but also it's cool. You know, we've been anticipating this and I feel like it's met expectations for sure. It's been fun. Aw, thank you, Sandy. So, anything we want to point out, guys?
No,
You want
I think energy is waning. Along with the moon.
What was that, Nancy? Belu?
Yes.
Okay, Dr. Bailey's coming over. Yeah, I'll switch. Yeah, I'll go this way. Musical chairs. We get the man himself.
They're looking at
Yeah,
this
just come right
picture?
here.
Yes. So this the eclipse curve, we are missing something in the lower bottom. So how do we use this eclipse curve is we make a derivative of this. That is why we need to have a good long baseline. That's why we still continue observing, because so that it is sort of flattening, because the region is completely outside the moon now. The moon has left the thing. So, but still, we want to get a good stable baseline so that we can interpret the data properly. So this is a very excellent data. So you can, if you had looked at it, at least even with the eyeball, you can say there have been 2 places where the gradient was higher. That means there must have been bright sources there. So at least certainly we are resolving 2 bright spots in this region. So that should almost complete our eclipse. We have 1 more region to do, and then we will be making some maps of the sun just to know the sun is there. Okay, the radio telescope. We need to do those maps because one of our calibration procedure used to use the quiet sun to calibrate the brightness scale. So what you see here is all counts, but then we have to convert it to a brightness temperature on the sun. So that for that calibration, we need the mapping process. And of course, mapping is always important to know how the region has changed, because we have observed this region yesterday, 5 times yesterday, and we couldn't do it this morning because the sun, there wasn't any time because the eclipse started almost close to sunrise. So we will make some maps. So we will compare it to see whether there have been any changes in the active region with the time. After all, it is changing constantly, these regions. That is one of the reasons why we study them, to study the evolution. And one important thing to study the evolution is what is important to us is the solar weather, the space weather caused by these active regions. How they do that? Because these active regions produce flares, and these flares produces a lot of energetic particles, and they reach the earth, and then they cause all this radio blackout and many of these space weather. So by looking at the evolution of these active regions, we can see whether what is their flare producing potential. I mean, it's very hard to, looking at the cloud, you cannot say it is going to rain always, but most time you can say that. But then, so our idea is to predict that with the collect. That's what the reason why we keep collecting a lot of data, and we need the citizen scientists, people outside, to look at a whole lot of data and build a large database. So
Yeah.
I think I have
See if we have any questions.
explained.
I think that's good. Any
Thank you.
questions for Dr. Vela? No, I don't think so. I'll call you
Thank
back.
you.
You can go back. He's busy. Yeah.
Like,
Good. Should we probably wrap up? Maybe. I mean, there's probably nothing else that we're going to really collect, right, team?
Yep.
What do you think about wrapping up? Okay. Well, we really appreciate everybody who's stuck with us the whole time. I think that we should have kept some winners.
Yeah. Thanks, Mom and Dad.
Yeah.
Sandy.
And Sandy. Joe's been on the whole time. So we've definitely had some folks. Thank you so much to Eileen. Are you still on? Eileen's still on. Thanks for being our correspondent in Texas. Thank you to all of you who have really contributed. Chris, we're looking forward to connecting about other kinds of STEM projects that we're doing. And then of course to our students, really looking forward to working with you to take a deeper dive and help you in your journeys to figure out what it is that you want to do. And maybe radio astronomy is part of it. And maybe it's not. Maybe it's just this is one way for you to look at teams, look at critical thinking, and use a really cool tool.
Yes.
Yeah.
Yeah. We don't all need to be radio astronomers, but we can all benefit from like knowing the scientific process that goes into taking these sorts of observations and doing this sort of science.
So thank you again. We hope to really work together a lot in the future. Don't forget mc@lcer.org, and happy rest of your day and weekend.
Yeah.
Right?
Thanks, everyone.
Okay. Thank you. Signing off.